Hello, and welcome to Sleepy Science. The speed of light is not simply the fastest speed in the universe. It is a boundary woven into reality itself, one that light can reach, matter can only approach, and nothing carrying information seems able to cross. But why does this limit exist? Why does every observer measure the same speed, no matter how quickly they move? And what would happen to time, distance, and cause and effect if this boundary could somehow be broken? Tonight, across 100 calming and thought-provoking questions, we will follow light to the edge of what physics allows and uncover why its speed may be hiding one of the deepest secrets in the universe. Before we begin, tell me where you are listening from and don't forget to like and subscribe. The speed of light is really the speed of cause and effect. Hidden beneath every movement in the universe is a rule more important than light itself. No physical influence can arrive before it has crossed the space between cause and consequence. The familiar value called the speed of light is therefore not merely the pace of photons racing through darkness. It is the maximum speed at which information, energy, or a change in a physical field can propagate through empty space. Light exposes this boundary because electromagnetic radiation naturally travels along the fastest paths spacetime permits, but the limit applies far beyond vision. When an electric charge changes direction, the disturbance in its field spreads outward rather than updating the entire universe at once. When two distant objects interact, each can respond only after some influence has had time to reach it. Even a perfectly rigid rod cannot exist, because pushing one end creates a compression wave that must travel atom by atom before the far end begins to move. This finite limit divides reality into regions that can influence one another and regions that remain temporarily disconnected. Without it, the order of events could become unstable. In some frames of motion, a faster-than-light signal could be received before it was sent, allowing a consequence to appear before its cause. Relativity protects causality by weaving this speed directly into the geometry of space and time. The limit is not like a traffic law that objects simply agree to obey. It is part of what distance, duration, and motion mean. That is why massive objects cannot be accelerated beyond it, and why every observer in uniform motion measures the same vacuum speed for light, even when they disagree about distances and clocks. The universe is not an arena in which information instantly appears everywhere. It is a vast network that updates itself at a finite pace. What you call the speed of light is therefore the speed at which reality is allowed to respond, the boundary preserving the difference between what has happened, what can affect you now, and what has not yet had time to arrive. You have never seen anything exactly as it exists right now. Your entire visual world is an extraordinarily convincing reconstruction of moments that have already passed. When you look at a face across the room, light reflected from that face must enter your eyes, activate the retina, travel through neural pathways, and be separated into features such as color, depth, shape, and motion before your brain combines them into a meaningful person. The travel time across a room is almost unimaginably brief, but biological processing is slower, requiring a small yet measurable fraction of a second. Conscious perception, therefore, does not sit directly on the sharp edge of the present. It follows behind, receiving incomplete signals and turning them into a smooth experience. Strangely, you rarely notice this delay because your brain does not behave like a camera waiting for every frame to arrive. It predicts. It uses the direction of a moving object, the rhythm of a voice, and the context of a scene to estimate what is probably happening now. Your senses also deliver information at different rates. Visual signals, sounds, and touches may reach the brain at slightly different moments, yet they are usually experienced as one unified event. When you watch someone clap their hands, your mind quietly aligns the movement and the sound, even though the information followed different physical and neural routes. This ability is essential because a mind that displayed raw sensory delays would experience reality as fragmented and unstable. The present you feel is instead assembled from a narrow window containing recent input, immediate memory, and prediction. That does not mean perception is false. It means perception is practical. Evolution did not build a system that reveals the world with perfect philosophical accuracy. It built one that helps you move, recognize danger, communicate, and survive. Every color you see is the brain's interpretation of wavelengths. Every stable object is identified from changing patterns of light. Every apparently continuous motion is constructed from signals processed over time. You never receive reality untouched, yet the reconstruction is so precise that you can catch a falling object and read emotion in a passing expression. The unsettling lesson is not that you are disconnected from the world, but that connection requires translation. You live just behind the physical present, inside a carefully edited version of it. And the feeling of now is the brain's best attempt to remain synchronized with a universe that never pauses for consciousness to catch up. If the sun vanished, Earth would not know for more than 8 minutes. For 8 minutes and roughly 20 seconds, humanity could live beneath the image of a sun that no longer existed. The sun cannot simply disappear under known physics, so this is a thought experiment rather than a realistic prediction. But it reveals exactly how Earth receives information from its star. The average distance between Earth and the Sun is about 150 million kilometers, and sunlight needs a little over 8 minutes to cross that gap. The sun you see in the sky is therefore not the sun of this exact instant. It is the sun as it was more than 8 minutes ago. If it could somehow vanish, the photons already traveling toward Earth would continue their journey. So daylight would remain normal until the final wave of sunlight arrived. Earth's orbit would also continue unchanged during that interval. General relativity does not describe gravity as an instantaneous invisible pull reaching across space. The sun shapes space-time around it, and any alteration in that gravitational environment would move outward rather than being felt everywhere at once. Until the change reached Earth, our planet would continue following the same curved orbit it had followed before. Then, at approximately the moment the final sunlight passed, Earth would stop orbiting the missing sun and continue moving along a path tangent to its former orbit. The planets would not all react together. Mercury would encounter the change sooner, while Jupiter, Saturn, and the more distant worlds would continue tracing their old paths for much longer, each responding only when the disturbance reached its location. On Earth, the first effect would be darkness rather than instant freezing. The atmosphere, land, and oceans contain stored heat, so temperatures would fall over time, although photosynthesis would stop almost immediately, and the long-term consequences for life would be catastrophic. The sky would still contain stars, and artificial lights would continue to function. But the central source that shaped climate, seasons, and nearly every ecosystem would already belong to the past. The thought is haunting because it exposes how distance delays knowledge. You do not experience distant objects as they are. You experience the last message that has reached you from them. For those final 8 minutes, Earth would continue living inside an outdated version of the solar system, responding faithfully to a star that was already gone. No matter how fast you chase light, it still moves away at the same speed. Imagine racing beside a beam of light in a spacecraft, moving so quickly that entire planets blur behind you, only to discover that the light is not drifting slowly ahead, as ordinary intuition predicts. It is still escaping from you at exactly the same vacuum speed, measured by someone who never began the chase. With cars, aircraft, or thrown objects, speeds normally combine. If you run after something moving ahead, its speed relative to you becomes smaller. Light refuses to follow that familiar rule. Every observer moving steadily through empty space measures the same speed for it, regardless of the motion of the source or the observer. This does not happen because light secretly accelerates whenever someone pursues it. Instead, space and time adjust the measurements that different observers make. Their clocks do not remain perfectly synchronized. Their measured distances do not remain identical. and their definitions of simultaneous events separate in just the right way to preserve the same result. Einstein recognized that this strange consistency was not an inconvenience to be explained away, but a clue about reality's structure. You could launch a flashlight from Earth from a fast spacecraft, or from an object rushing toward you, and although the light's color and energy might change, its vacuum speed would not. Even if you reached 99% of that speed, the remaining difference would not feel like the final 1% you could casually overcome. The geometry of space-time would keep the light moving away from you at the same fundamental rate. This is why there is no valid resting viewpoint from which you can hover beside a photon and watch a frozen wave of light. The closer a massive traveler comes to that boundary, the more dramatically measurements of time, distance, and energy must differ from those of slower observers. Light is therefore not merely an object moving unusually fast through an ordinary universe. Its constant speed reveals that the universe changes how motion itself is measured. You may chase the beam as far as technology and energy allow, but nature will never let you pull alongside it, as though light forever marks a horizon that motion can approach, but no massive traveler can share. The universe has no single present moment shared by everyone. Somewhere far beyond Earth, two events may be happening that you confidently call simultaneous, while another observer moving past you can truthfully say that one occurred before the other. This is not a delay caused by poor instruments, nor an illusion created because news takes time to travel. It is a genuine feature of space-time known as the relativity of simultaneity. To define what is happening right now at distant locations, you need clocks placed throughout space and a method for synchronizing them. Observers moving together can perform this task consistently within their own frame, but observers moving differently will not agree that the same distant clocks are synchronized. A classic way to understand this is to picture flashes occurring at the front and rear of a moving train. A person standing beside the tracks may receive the two flashes together and conclude that they happened at the same time. A passenger moving toward one flash and away from the other might initially seem to disagree merely because the light reaches them at different times. But relativity goes deeper. After correctly accounting for the travel time, the passenger's system of synchronized clocks still assigns the flashes different times. Neither observer has made a mistake. They divide spacetime into past, present, and future along different slices because they are moving differently. Nearby events remain simple enough for everyone to agree on their causal order, especially when one can physically influence the other, but widely separated events that cannot exchange a signal quickly enough to be causally connected possess no universal ordering. One observer may say a distant star changed before a spacecraft transmitted a message. Another may say the transmission came first, and both descriptions can be physically valid as long as neither event caused the other. At ordinary human speeds, these disagreements are far too small to notice. So daily life encourages the comforting idea that one invisible cosmic clock is ticking everywhere. Relativity removes that clock. Cosmologists can define a useful cosmic time tied to the average expansion of the universe, but it is not an absolute present imposed on every possible observer. The universe does not unfold as one perfectly synchronized stage. It is a four-dimensional structure in which each observer carries a different way of grouping distant events into moments. Your now is real for you, yet it does not stretch unchanged across the cosmos. And perhaps the present feels so precious precisely because nature never promised that everyone, everywhere, must share it. The faster you move through space, the slower you move through time. A clock carried on a sufficiently fast journey will return having recorded less time than an identical clock left behind, even though neither clock ever feels damaged, delayed, or unusual while the journey is taking place. This effect, called time dilation, is not a flaw in mechanical clocks. It applies to every physical process inside the moving system. Heartbeats, chemical reactions, atomic vibrations, and aging all proceed normally from the traveler's own perspective. Yet an observer relative to whom that traveler is moving measures those processes as unfolding more slowly. The effect is tiny at the speeds of cars and aircraft, which is why you can cross a continent without noticing a meaningful difference in your age. But it becomes dramatic as motion approaches the speed of light. Scientists have confirmed it using extremely precise atomic clocks carried on aircraft and satellites, and nature demonstrates it continuously through unstable particles called muons. Many muons are created high in the atmosphere when cosmic rays strike molecules. At rest, they decay so quickly that most should disappear before reaching the ground. Yet because they travel close to light speed, far more survive the journey than ordinary timing would predict. From Earth's frame, their internal clocks run slowly. From the muon's frame, the atmosphere is shortened along their direction of motion. Both descriptions lead to the same observed arrival. It is tempting to say that motion somehow steals time, but the deeper explanation is that space and time are not independent containers. They form one connected structure, and observers following different paths through it can accumulate different amounts of elapsed time between meetings. Speed does not make you feel frozen, nor does it give you a universal advantage over everyone else. Motion is relative, and simple constant motion alone cannot identify one person as absolutely stationary. A lasting age difference appears when travelers take different routes through spacetime and later reunite, often because one of them changes direction or undergoes acceleration. Then their clocks can be placed side by side and compared without debate. The faster journey may have crossed enormous distances, while only a modest interval passed for the traveler, allowing voyages that seem impossibly long from Earth to feel much shorter on board. Yet there is no hidden pause inside the spacecraft. Thoughts continue, breath continues, and every second feels complete. What changes is not your experience of each moment, but how many moments fit along your path before it meets another path again. Motion does not merely carry you through space, it quietly changes the amount of future you personally reach. Anything with mass would need infinite energy to reach the speed of light. The final fraction of the journey toward light speed is not merely difficult, it becomes physically unreachable for anything that carries mass. At low speeds, adding energy produces an obvious increase in motion, much like pressing harder on a vehicle and watching it accelerate. But as a massive object moves faster and faster, the relationship changes. More of the added energy increases the object's total relativistic energy and momentum, while each new push produces a smaller gain in speed. Reaching 90% of light speed is demanding. Moving from 99% to 99.9% demands vastly more energy, and every additional 9 raises the cost again. The speed can approach the limit endlessly, but it cannot complete the final step. To reach light speed exactly, a massive spacecraft, particle, or human body would require an unlimited amount of energy, more than any engine, star, or civilization could supply. This does not mean the object's ordinary rest mass literally grows in the modern description. Rather, its resistance to further acceleration appears through its increasing energy and momentum. Particle accelerators demonstrate this clearly. They pour enormous amounts of energy into protons and electrons, bringing them extraordinarily close to light speed. Yet the particles never cross or touch the boundary. Their speed changes only slightly while their energy continues to rise dramatically. Massless particles begin on the other side of this rule. In empty space, they do not need to accelerate up to light speed because they can only exist while moving at that speed. A massive traveler, however, is confined to a different class of motion. The barrier is therefore not a weakness of engineering waiting for a better fuel. It is built into the structure of space-time itself. You could gather the power of planets, surround a ship with engines, and continue accelerating for ages, yet the last step would always retreat before you. Nature allows you to move ever closer to the boundary, while ensuring that the boundary never becomes a destination. Along a ray of light, no proper time passes between emission and arrival. A photon can leave a star billions of light years away and reach a telescope on Earth along a path for which the measured proper time is exactly 0. This statement sounds as though light experiences the entire journey instantly, but that familiar wording must be handled carefully. because physics does not allow a valid resting frame for a photon. You cannot imagine attaching a clock to light, traveling beside it, and asking what it sees. The mathematical rules used for ordinary observers break down at that limit. What can be said precisely is that space-time assigns no proper time interval to a light-like path. Proper time is the duration recorded by a clock moving along a particular route, and for any object with mass it advances normally, whether the object is resting, walking, or crossing interstellar space. Light follows a different kind of route, called a null path, in which the separation through space and the separation through time balance in a unique way. Earth may record seconds for a laser pulse, years for light from a nearby star, or billions of years for radiation from the early universe. Yet the geometric interval along the ray remains zero. This does not erase the enormous distance or make the emission and arrival the same event. The star can change, planets can form, and civilizations can rise while the light is in transit according to ordinary observers. The zero belongs not to our clocks, but to the structure of the path connecting the two events. This distinction reveals why phrases such as, "from the photon's perspective," are tempting but misleading. A perspective requires a physical observer with a clock and a rest frame, and light has neither. Still, the mathematics points towards something deeply unfamiliar. The universe can contain journeys that span vast regions of space and immense stretches of cosmic history without accumulating proper time along the route itself. Light does not carry an internal clock slowly ticking across the darkness. It simply connects one event to another along the edge where ordinary notions of elapsed time no longer apply. Distant galaxies can, separate from us, faster than light without breaking relativity. Far beyond the nearby galaxies, there are regions of the universe receding from us faster than a beam of light could cross the same distance. Yet no galaxy there is locally racing through space in defiance of relativity. The key is that cosmic expansion is not an explosion sending galaxies outward from one central point. On the larger scales, the space between widely separated galaxies stretches, increasing their distance even when each galaxy remains nearly at rest within its own local region. A small amount of expansion across one short interval of space is modest, but across billions of light years, those small increases accumulate. The result is a recession rate that can exceed the speed of light for sufficiently distant objects. Relativity forbids matter and information from moving through nearby space faster than light, but it does not place the same simple limit on how quickly the total distance between remote regions can grow as space-time expands. No astronaut standing beside one of those galaxies would watch neighboring stars shoot past at impossible speeds. Locally, light would still move normally, and every nearby physical law would remain intact. The faster-than-light separation appears only when distances are compared across the expanding cosmos. This also explains a surprising fact. Astronomers can sometimes observe galaxies that are currently receding faster than light. The photons we receive were emitted when those galaxies were closer and when the expansion conditions along the route were different. As the light traveled, it crossed regions whose expansion rate changed over cosmic history, eventually reaching us despite the galaxy's present recession. Other galaxies are so distant that light emitted by them today may never overcome the growing space between us. They have not broken the speed limit. The route itself is being stretched too quickly. Cosmic expansion therefore reveals that moving through space and being carried apart by expanding space are not the same phenomenon. The universe can enlarge the distance between two places faster than light could traverse that distance, while preserving the local rule that no object overtakes a nearby light beam. What seems like a contradiction disappears once you realize that space-time is not a fixed stage beneath the galaxies. It is part of the evolving performance. Some galaxies are already beyond humanity's reach forever. There are galaxies whose light can still enter your telescope, even though no spacecraft launched today, or at any time in the future, could ever reach them. The reason is not that they are simply too far away in the ordinary sense, but that the universe is expanding in a way that creates a boundary between what can be observed and what can still be visited. A galaxy may have sent out the ancient light we now receive when it was much closer to us, allowing that light to begin a journey that eventually reaches Earth. But during the billions of years since those photons departed, the space between us and the galaxy has continued to grow. If cosmic expansion keeps accelerating as current evidence suggests, a spacecraft leaving now would find the remaining distance increasing so quickly that no amount of ordinary travel time could close the gap. Even a ship moving arbitrarily close to light speed would remain confined by the future structure of spacetime. This boundary is sometimes described as a cosmic event horizon, not a wall you could see or collide with, but a limit beyond which events occurring now can never send signals that will reach us. The observable universe and the reachable universe are therefore not the same thing. You can see ancient images of places you can never visit, much as you might receive a final letter from a shore already being carried beyond every possible route. Over immense timescales, more galaxies will cross this horizon, and their newest light will cease to arrive. They will slowly fade from our future sky, not because they have stopped existing, but because the expanding universe has removed them from any possible exchange of information. Humanity may one day build machines far beyond anything imagined today, yet technology cannot overcome a destination that space-time itself prevents from remaining connected to us. The haunting truth is that the cosmos contains visible places already lost to every future journey, and the light entering your eyes may be less an invitation than a farewell, sent billions of years before anyone was here to understand it. Every mirror shows you a version of yourself from the past. The face in your mirror has already disappeared by the time you see it. Light must leave a source, strike your skin, reflect toward the glass, bounce back, and finally enter your eyes before an image can form, so even the closest mirror can only show a slightly earlier version of you. The delay is extraordinarily small, only a few billionths of a second for a mirror within arm's reach, but it is physically real. Move the mirror farther away and the delay grows because the light must complete a longer round trip. A mirror placed roughly 150,000 kilometers away would show you as you appeared about 1 second earlier, assuming an image could be transmitted clearly across that distance. At everyday scales, this difference is too brief for your brain to notice, so the reflection seems perfectly synchronized with your movement. You lift a hand, and the image appears to lift its hand at once. Yet the mirror is not copying the present. It is returning old information so quickly that your nervous system accepts it as immediate. The image also carries another subtle deception. A flat mirror does not literally swap left and right. It reverses the direction perpendicular to its surface, turning front into back, while your mind interprets the reflected figure as though another person had rotated to face you. This is why writing appears reversed even though the top and bottom remain unchanged. The mirror is therefore neither a window nor a stored photograph. It is a device that redirects traveling light, continuously constructing an image from information that has just completed a journey. Every time you look into one, you are observing a history so recent that it feels like the present. You can never catch your reflection exactly as it is now, because the act of seeing always requires something to leave you, travel away, and return. The person in the glass is undeniably you, but it is also someone you have already become too late to meet. A conversation with someone on the moon can never feel truly instant. Ta'amaimed. Person standing on the moon could hear your question only after a silence that no faster computer, clearer microphone, or stronger radio transmitter could remove. The moon is about 384,000 kilometers from Earth on average, so a radio message takes roughly 1.25 seconds to travel one way. A simple question and answer therefore creates a minimum round-trip delay of about 2.5 seconds, before either person has spent any time thinking or speaking. That gap may sound small, but human conversation depends on timing measured in fractions of a second. You normally use tiny pauses, quick interruptions, changes in tone, and immediate reactions to judge whether someone understands, disagrees, or is about to continue. Across lunar distance, those cues become detached from the moments that created them. You might ask a question, wait, and begin speaking again just as the other person's answer finally reaches you. They may interrupt a sentence you already finished several seconds ago, while you respond to words they no longer remember delivering in quite the same emotional state. Apollo mission recordings reveal this unusual rhythm. Instructions are followed by unavoidable silence. Then confirmation arrives after the physical event has already moved forward. Engineers can reduce equipment delays, improve compression, and predict routine responses, but they cannot erase the travel time through space. This has practical consequences as well as emotional ones. A machine on the moon cannot always be steered as naturally as a vehicle beside you, because every command arrives late and every camera image shows what was happening more than a second earlier. Autonomous systems become valuable, not because radio communication fails, but because distance makes constant human correction clumsy. A lunar conversation would still be possible, intimate, and recognizably human, yet it would require patience and a different rhythm of attention. Each person would be speaking into a brief silence, trusting that the other voice was already on its way. The moon appears close enough to touch in the night sky, but a real conversation with someone standing there would reveal the distance more clearly than any photograph, not as empty kilometers, but as time inserted between one mind and another. Humans on Mars could never be controlled from Earth in real time. The first humans on Mars will be farther beyond immediate help than any explorers in history, not because Earth will be unable to hear them, but because every message will arrive too late to control what they are doing. As Earth and Mars move around the Sun, the one-way communication delay changes from roughly 3 minutes at their closest useful alignment to more than 20 minutes when they are far apart, creating a round-trip delay that can approach 45 minutes. A controller on Earth could not guide an astronaut's hand during a repair, steer a rover around a sudden obstacle, or talk a doctor through a medical emergency as it unfolds. By the time a warning reached Mars, the dangerous moment might already be over. By the time the crew's response returned, Earth would be receiving news from a situation that had changed again. This means a Martian settlement could not function like a remote base waiting for constant instructions. Its people would need authority to make decisions locally, machines capable of navigating and diagnosing problems on their own, and training broad enough to handle failures that specialists on Earth could only examine afterward. Even ordinary conversations would take on the rhythm of recorded letters rather than live dialogue, with each person sending complete thoughts into a silence that might last many minutes. During certain alignments, when the Sun lies between the planets, radio communication can become disrupted enough that missions reduce or pause commands for days. Mars exploration is therefore not only a challenge of rockets, oxygen, and radiation, it is a challenge of independence. The farther humans travel from Earth, the less exploration resembles operating a distant machine, and the more it becomes the creation of another decision-making world. The first Martian crews may still depend on Earth for knowledge and emotional support, but in the moments that matter most, they will have to act without permission, carrying the full weight of being the only humans close enough to save themselves. Even the fastest internet connection is limited by the size of the planet. A message sent across Earth may seem instantaneous on your screen, yet the planet itself places a delay beneath every video call, online game, financial trade, and cloud service. Data travels through fiber optic cables as pulses of light, but inside glass, those pulses move significantly slower than light does in empty space, typically at around 2/3 of its vacuum speed. The route is also rarely a straight line. Submarine cables curve around coastlines and hazards, while data may pass through routers, switching centers, security systems, and crowded networks before reaching its destination. Even if every computer and cable worked perfectly, a signal crossing an ocean would still need measurable time simply because thousands of kilometers lie between sender and receiver. This physical limit is why a server located near you can feel more responsive than an identical one on another continent. and why competitive gaming companies, streaming platforms, and financial firms place data centers close to their users. Engineers can reduce delays by choosing shorter routes, improving equipment, storing popular content locally, and predicting what users may request next. But they cannot make information cross Earth in zero time. Satellite networks can shorten some routes by sending signals through near vacuum rather than long fiber paths, although the climb to space and movement through ground stations introduce other delays. The internet therefore does not erase geography. It disguises it through speed, caching, and careful design. When a website opens quickly, you may be receiving a nearby copy rather than information freshly delivered from the other side of the world. The modern network feels like one shared digital room, but beneath that illusion is a planet of fixed dimensions, forcing every packet to travel a real path. No future processor can negotiate with distance itself, and the faster our technology becomes, the more clearly the remaining delay reveals the shape of the world carrying it. In 1 nanosecond, light travels only about 30 centimeters. A billionth of a second sounds too small for anything meaningful to happen, yet during that interval, light cannot even cross the length of an ordinary desk. In empty space, it travels about 30 centimeters in 1 nanosecond, and through wires or circuit materials, the effective progress of an electrical signal is often slower. This tiny distance becomes surprisingly important inside modern technology, where processors perform billions of timing cycles each second. If a signal must travel several centimeters across a chip, through a circuit board, or between separate components, its journey can consume a noticeable portion of the available time before the next operation begins. Engineers cannot simply make a computer infinitely faster by increasing its clock rate, because information must still move through physical materials. Transistors require time to switch, and heat rises as more operations are compressed into each second. At these scales, a wire is not merely a passive connection. Its length, shape, and surrounding material can alter when a signal arrives and whether it remains clean enough to interpret. This is one reason powerful processors place frequently used memory extremely close to their computing cores, and why large machines divide work among many units rather than depending on one endlessly accelerating center. The 30-centimeter rule also gives a strange physical scale to time. 1 nanosecond is not only a number on an instrument, it is approximately the time needed for light to move from your hand to your shoulder. A microsecond allows light to travel hundreds of meters, while a millisecond is long enough for it to cross hundreds of kilometers in vacuum. The faster technology becomes, the less time feels abstract, and the more it becomes a measurable distance. What seems like an almost non-existent instant still has boundaries, and even light, the fastest messenger nature permits, must spend that instant going somewhere rather than being everywhere at once. Every event in the universe is trapped inside a light cone. The moment you move a finger, ignite a candle, or form a single spoken word, the event does not become part of the entire universe at once. It begins inside an invisible boundary called a light cone. Picture one point in space-time opening into two widening regions. A future cone containing every place that signals from the event could eventually reach, and a past cone containing every earlier event that could have influenced it. A flash produced beside you can affect nearby objects almost immediately, reach the moon after a little more than a second, and cross interstellar distances only after years, so the cone widens as time passes. Anything outside it is not merely far away, it is causally unavailable. No message, warning, particle, or physical disturbance from the event has had enough time to arrive there. This creates a third region, sometimes called elsewhere, filled with distant events that cannot yet influence one another. Two explosions separated in this way may be assigned different orders by observers moving differently, but neither can be the cause of the other, because no signal could have crossed the gap. Light cones therefore provide the hidden map behind every possible chain of events. Your decisions can shape only what lies inside your future cone, while everything that has helped create this moment must lie somewhere inside your past cone. As you sit quietly, your future cone is expanding through the room, through Earth, and eventually toward the stars, carrying the possibility that something you do now may leave a trace far beyond your lifetime. Yet most of the cosmos remains outside your immediate causal reach. You exist not at the center of everything, but at the tip of a temporary opening, surrounded by regions reality has not yet allowed you to touch. Every event is free to send consequences forward, but only along paths that fit inside its cone, as though the universe permits possibility to grow while still giving it an edge. Faster than light travel could allow an effect to appear before its cause. Spacecraft that outran light would not simply arrive somewhere unusually early. Under the rules of relativity, it could arrive before some observers believed it had departed. The problem begins because observers moving relative to one another do not always agree on the timing of distant events. For ordinary slower-than-light motion, these disagreements never reverse a genuine chain of cause and effect. Everyone agrees that a signal was sent before it was received. A faster-than-light signal would cross the boundary that protects this order. In one frame of motion, a message might leave Earth and then reach a passing spacecraft, while in another valid frame, the reception could be assigned an earlier time than the transmission. That alone does not automatically create a paradox, but the danger becomes real if the recipient sends a faster-than-light reply. With the right arrangement of relative motion, the answer could return to Earth before the original message was sent. You might receive a warning telling you not to transmit the message that produced the warning. If you obey, no warning should exist. If no warning exists, you may send the message after all. This imagined device is sometimes called a tachyonic anti-telephone, and it demonstrates why faster travel is inseparable from time travel within special relativity. The difficulty is not merely that present technology lacks a powerful enough engine. The deeper problem is that exceeding the causal boundary allows closed loops in which information becomes part of its own origin. Proposed ideas such as warp geometries and wormholes try to avoid locally pushing matter through space faster than light, yet many versions still risk producing the same causal loops when their endpoints move or are arranged in particular ways. Physics may possess some still unknown mechanism that forbids these situations, perhaps through instability or impossible energy requirements. Until then, the speed limit appears to protect more than motion. It prevents a sentence from becoming its own author and keeps the universe from receiving answers to questions that have not yet been asked. Gravity does not act instantly. Its changes travel at the speed of light. Two black holes can spiral together in a distant galaxy, violently disturb spacetime, and send that disturbance across the cosmos as a traveling gravitational wave rather than an instantaneous command felt everywhere. In Einstein's description, gravity is not a rigid, invisible rope connecting masses. Matter shapes spacetime, and when massive objects accelerate or rearrange themselves, changes in that geometry propagate outward at a finite speed. This was directly tested in 2017 when gravitational waves from the merger of two neutron stars reached Earth, followed less than 2 seconds later by high-energy light from the same general event after traveling for about 130 million years. The small arrival difference was consistent with the light being produced or delayed by the complex explosion, while the long shared journey showed that gravitational waves and light travel at extraordinarily similar speeds. Yet a subtle question remains. If gravity is delayed, why does Earth not orbit the position where the Sun used to be several minutes earlier and slowly spiral out of control? The answer is that a gravitational field contains information not only about an object's old position, but also about its motion, and the velocity-dependent parts of the field largely prevent the simple lag your intuition might predict. In a stable system, the resulting attraction points in the dynamically correct direction rather than behaving like a delayed rope. Only changes, such as accelerating masses or shifting distributions of matter, carry genuinely new gravitational information outward. Binary pulsars provide another clue. Their orbits gradually lose energy at precisely the rate expected, when gravitational waves carry energy away. Gravity therefore has memory, motion, and propagation. It does not refresh the cosmos as one simultaneous picture. It moves changes through space-time in expanding ripples. The ground beneath you feels steady because Earth's gravitational environment changes slowly, but far away. Colliding stars are continually writing new distortions into the universe. Those distortions travel through darkness for millions of years before causing mirrors in a detector to move by less than the width of a proton, allowing you to hear not gravity acting instantly, but space-time arriving with news from its own distant past. Gravitational waves and light cross the universe at nearly the same cosmic speed. Two messengers can leave the same cosmic catastrophe in completely different forms, one as light moving through electromagnetic fields, the other as a ripple passing through the structure of space-time, and still cross an immense universe at almost exactly the same speed. This agreement is far more important than it first appears. Light can be absorbed, scattered, delayed by matter, or hidden behind dust, while gravitational waves pass through planets, stars and gas with almost no disturbance, carrying information from violent regions that ordinary telescopes may struggle to see. Yet when both signals travel through empty space, general relativity predicts that their fundamental propagation speed should be the same. Astronomers can test this by comparing signals associated with the same distant event and asking whether one arrives suspiciously earlier than the other after traveling for millions or billions of years. Even a microscopic difference in speed would accumulate into a large separation over such distances, so close arrival times place extremely strict limits on many alternative theories of gravity. Some theories once proposed that gravitational disturbances might travel more slowly, move through extra fields, or interact with a hidden cosmic medium. Observations have ruled out many of those possibilities or forced them into much narrower forms. Still, scientists must be careful. Two signals may not be created at precisely the same moment inside an explosion, and light can be delayed while escaping dense matter, so arrival differences do not automatically reveal different travel speeds. The deeper lesson is that light and gravity are not identical phenomena, yet space-time appears to grant them the same ultimate road through the cosmos. One reveals how charged matter shines, the other reveals how mass moves and space bends. Their shared speed suggests that the universe has a common causal structure beneath forces that otherwise seem entirely different, as though reality allows many kinds of messages, but insists that its fastest messengers obey one ancient rhythm. Matter is defined using the speed of light. The length of every ruler on Earth is ultimately tied to something no ruler can contain. The distance light travels through empty space during a precisely specified fraction of a second. For centuries, the meter was connected to physical objects and to the dimensions of Earth. One early definition attempted to make it a fixed fraction of the distance from the equator to the North Pole, and later scientists created metal bars intended to preserve the standard. But physical objects are imperfect guardians of measurement. They can expand with heat, contract with cold, become scratched, gather contamination, or change subtly over time. Modern metrology solved this problem by reversing the old relationship between length and light. Instead of measuring the speed of light using a meter that might change, scientists fixed the vacuum speed of light at an exact value and defined the meter from it. The second is established using an extremely stable transition in cesium atoms. And once time is defined with that precision, distance can be realized by measuring how far light travels during a chosen interval. This does not mean laboratories need to watch a pulse cross a full meter every time they calibrate an instrument. They often use lasers, interference patterns, and carefully controlled frequencies to reproduce lengths with extraordinary accuracy. The result is a unit that is no longer dependent on one treasured bar stored in a vault. Any capable laboratory can reconstruct the meter by referring to the same physical constant and atomic time standard. This makes measurements more universal, reproducible, and resistant to the aging of objects. The table in front of you, the dimensions of a spacecraft component, and the microscopic features etched onto a computer chip are all measured within a system anchored to light and atomic behavior. A meter may feel like an ordinary piece of space, but its modern meaning is woven from time, radiation, and a constant believed to be the same throughout the universe. Humanity did not merely create a better ruler. It learned to define length using the dependable behavior of nature itself. Massless particles cannot slow down or stop in empty space. Try to imagine a photon gradually becoming tired, slowing through empty space, and finally resting beside you like a grain of dust. The picture seems harmless. But relativity does not permit such a state to exist. A truly massless particle cannot be stationary in vacuum, nor can it move at any ordinary speed below the universal limit. Its existence is tied to motion at that speed. Massive objects can rest because they possess energy even when they are not traveling, and they can be accelerated through a continuous range of slower speeds. A massless particle has no such resting condition. If you reduce a photon's energy, you do not make it crawl more slowly. You change its frequency and wavelength. A lower energy photon may become red light, infrared radiation, a microwave, or a radio wave, yet every one of these still moves at the same local vacuum speed. Increase the energy, and it may become ultraviolet light, an X-ray, or a gamma ray, but again the speed remains unchanged. This is why color does not represent how fast light is traveling through empty space. When light appears slower inside glass or water, the delay comes from its interaction with the material's charged particles and from the way the combined wave propagates through the medium, not because an isolated photon has adopted a stable, slower vacuum speed. A photon may also be absorbed, transferring its energy to matter, but absorption is not the same as stopping while remaining a free photon. The particle ceases to exist as that traveling photon, and its energy becomes part of another physical system. Other massless particles, should they exist freely, would face the same relativistic rule, although some particles described as massless in theory cannot travel independently because they are confined by their interactions. The important divide is therefore not simply between fast and slow objects, but between entities that can possess a rest frame and those that cannot. Light does not race because it has been powerfully accelerated. It moves as it does because a slower version of a free photon is not one of the states the universe allows. Light has momentum, even though it has no rest mass. A beam of light can strike an object and make it recoil, even though the light carries no rest mass at all. This seems impossible only because everyday intuition teaches you to connect momentum with heavy things in motion, a rolling stone, a speeding car, or a falling hammer. But momentum is not owned by mass alone. Light carries energy, and in relativity, energy itself can carry momentum through space. A photon with higher energy carries more momentum than a lower energy photon, which means blue or ultraviolet light transfers more momentum per photon than red or infrared light. You can see the consequences in laboratories when light strikes atoms and gives them tiny kicks, changing their motion in measurable ways. This recoil is essential in techniques that use lasers to slow and cool atoms, where carefully directed photons repeatedly push against moving particles until their motion becomes extraordinarily small. The same principle appears in the Compton effect, where an energetic photon collides with an electron, changes direction, loses some energy, and transfers momentum to the electron, much like one moving object striking another. Yet the photon never needed rest mass to participate in the collision. Its energy and direction were enough. Light can also exert pressure on larger surfaces. If a surface absorbs a photon, it receives the photon's forward momentum. If the photon reflects, the momentum transfer is greater because the photon reverses direction and the surface must take up the difference. For ordinary lamps, this pressure is far too weak for your hand to notice, but precise instruments can detect it, and around brilliant stars, it can influence dust, gas, and even the shape of comet tails. This helps reveal a deeper truth about matter and radiation. The universe does not divide neatly into heavy objects that can push and weightless light that can only illuminate. A photon has no rest frame and no rest mass, yet it transports energy, produces recoil, and changes the motion of whatever absorbs or redirects it. Light is therefore not a passive picture traveling through space. Every beam carries a faint mechanical presence, and every time illumination reaches matter, something more than visibility is exchanged. A sealed box becomes slightly heavier when light is trapped inside it. Place light inside a perfectly sealed, perfectly reflecting box, and the entire box becomes heavier, even though no new particle with rest mass has been added. The increase would be unbelievably small, but it follows directly from the relationship between energy and mass. A closed system's mass depends on all the energy contained within it, not only on the rest masses of its individual components. If a lamp inside the box converts stored chemical or electrical energy into light, the box does not suddenly gain mass because the energy was already present in another form. But compare two otherwise identical boxes, one empty and one supplied with additional trapped radiation, and the box containing more total energy has slightly more mass. Its weight in a gravitational field would also increase by the corresponding tiny amount. This does not mean each photon has acquired rest mass while bouncing between the walls. The photons remain massless, but the combined system of box, walls, and trapped radiation possesses more internal energy, and that energy contributes to the system's total mass. The light repeatedly strikes the walls, transferring momentum in changing directions. Yet when the whole sealed box is considered, those internal motions balance. From outside, the energy remains confined within one object, and the object resists acceleration slightly more than it would without that energy. The same reasoning applies to heated objects. A hot object has marginally more mass than the same object after it cools, because its atoms contain more thermal energy. A compressed spring, a charged battery, and an excited atom also have slightly more mass than their lower energy versions. The changes are normally far too small for household scales, but they are physically real. This turns the sealed box into more than a clever puzzle. It shows that mass is not simply a count of material pieces. It is a property of the total energy and internal structure of a system. What feels like empty radiance can contribute to inertia and weight when it is confined. The box becomes a quiet lesson in how relativity joins concepts that ordinary experience keeps separate. Heat, motion, radiation, stored energy, and mass are not isolated substances, but different ways a physical system carries the capacity to resist change. Light can push a spacecraft without touching it. A spacecraft can cross interplanetary space with no fuel burning behind it, driven only by sunlight falling on a vast reflective sail. The force is gentle because each photon transfers only a tiny amount of momentum. But sunlight arrives continuously, and in the near vacuum of space, there is little resistance to erase the accumulated motion. A solar sail works best when its surface reflects rather than merely absorbs incoming light. Absorption gives the sail the photon's forward momentum, while reflection sends the photon back in another direction and produces a larger change in momentum, giving the sail a stronger push. The acceleration may begin almost imperceptibly, yet it continues for as long as useful sunlight reaches the sail. A chemical rocket produces an enormous force for a limited time and must carry propellant that makes the vehicle heavier. A solar sail produces a weak force for months or years without consuming onboard reaction mass. By tilting the sail, navigators can change the direction of the pressure and gradually alter the spacecraft's orbit. The craft does not have to move directly away from the sun. Carefully chosen angles can make it gain orbital energy, spiral outward, reduce orbital energy, or change its inclination. Several missions have already demonstrated controlled solar sailing, proving that radiation pressure can serve as more than a theoretical curiosity. The design still faces serious challenges. The sail must be extremely large, light, reflective, and thin, yet strong enough to unfold without tearing. Sunlight weakens with distance, so a sail becomes less effective far from the sun unless powerful lasers or other external beams are used. Interstellar concepts imagine directing an intense laser array toward a very small sail, accelerating a lightweight probe to a significant fraction of light speed without forcing the probe to carry its own massive fuel supply. Such plans remain technologically difficult, but the principle is sound. No wind fills the sail, and no invisible gas pushes it forward. The spacecraft moves because light changes direction when it meets the reflective surface, and the sail must receive the balancing momentum. What appears weightless and untouchable becomes a method of propulsion, showing that even the quiet glow of a star can act like an engine when patience replaces combustion. Motion can stretch light into red or compress it into blue. A star does not need to change its temperature for its color to shift before your eyes. Motion alone can stretch the light it sends into redder wavelengths or squeeze it toward blue. This is the relativistic Doppler effect, and it begins with the wave-like rhythm carried by light. When a luminous object moves away from you, each new crest is emitted from a position slightly farther away than the one before it, so the arriving pattern is spread out. The wavelength becomes longer, the frequency falls, and the light is redshifted. When the source approaches, the crests arrive more tightly packed, producing shorter wavelengths and a blue shift. Unlike the familiar change in the pitch of a passing siren, light does not need air or any other medium, and its Doppler shift is shaped not only by changing distance, but also by relativity's treatment of time. Even motion across your line of sight can create a redshift because a rapidly moving source's processes are measured as running more slowly from your frame. Astronomers use these shifts as one of their most powerful tools. By studying the dark absorption lines and bright emission lines within a spectrum, they can identify familiar atomic fingerprints and measure how far those patterns have moved from their laboratory wavelengths. In this way, they discover whether a star is approaching or receding, map the rotation of galaxies, detect stars wobbling under the pull of unseen planets, and follow gas racing around compact objects. The effect can also alter more than visible color. Radiation moving toward you can be shifted from radio waves into microwaves, from visible light into ultraviolet, or from X-rays into even more energetic forms, while radiation moving away can fade into lower energy bands. At extreme relative speeds, an object's appearance would therefore be transformed, not because the object itself had suddenly become hotter or colder, but because your motion changed the rhythm at which its light reached you. Color, in this deeper sense, is not always an intrinsic label attached permanently to a source. It can be a relationship between the source and the observer, a record of whether the distance between them is opening or closing. The universe writes motion into light before that light enters your eyes, allowing a spectrum to preserve the quiet evidence of journeys you were never there to witness. Near light speed, the universe would collapse into a bright cone ahead of you. The stars would not simply streak past the windows of a near light speed spacecraft. Much of the visible universe would appear to gather into a brilliant, distorted region directly ahead. This effect arises from relativistic aberration, which changes the apparent direction from which incoming light reaches a rapidly moving observer. Light that originally approached from the sides, and even from parts of the sky somewhat behind the traveler, would be seen at angles shifted toward the direction of motion. As the spacecraft moved faster, a larger portion of the celestial sphere would seem compressed into a narrower forward cone, while the region behind would appear increasingly empty and dim. The effect is not caused by stars physically moving into a cluster in front of the ship. It is a transformation of how directions are measured when the observer moves at an extreme speed. At the same time, relativistic beaming would concentrate more received energy into the forward region. Light ahead would become blue shifted and intensified, while light from behind would be red shifted and weakened. Familiar visible stars might shift into ultraviolet or X-ray wavelengths, disappearing from human vision even as their radiation becomes more dangerous. Behind the craft, visible light might slide into infrared or radio frequencies, making the sky seem darker without the sources actually fading. The cosmic microwave background, normally detected as faint microwave radiation arriving from every direction, could be compressed and boosted ahead of the traveler until part of it reached far more energetic wavelengths. This means the view would not resemble the gentle star trails often shown in fiction. Depending on the speed, the forward sky could become a harsh concentration of radiation requiring heavy shielding, while navigation by ordinary visible constellations would become profoundly difficult. Dust grains and thin interstellar gas would also strike the craft with greatly increased energy, turning even sparse matter into a serious engineering hazard. Yet inside the ship, local vision, thought, and motion would still feel normal. The transformation would appear in the outside universe, which would seem to narrow around the direction of travel, as though the cosmos were being drawn toward a single luminous opening. Near the ultimate speed limit, your destination would not merely lie ahead of you. Much of the sky would appear to bend toward it, turning motion itself into a lens that reshapes where the universe seems to be. A fast enough journey can make interstellar distances physically contract. A voyage to a star many light years away can be shorter for the traveler without the star moving closer in Earth's own measurements. The reason is length contraction, a real relativistic difference in the distance measured between objects moving relative to an observer. Suppose Earth and a distant star remain at rest with respect to one another. Scientists on Earth can place synchronized clocks throughout their frame, measure the locations of both objects at the same Earth time, and assign a fixed distance between them. A spacecraft passing at an extreme speed uses a different set of synchronized clocks and a different definition of which separated events occur simultaneously. When the traveler measures Earth and the star at one spacecraft time, the distance between them is smaller along the direction of motion. Nothing is crushed, folded, or mechanically squeezed. The space between the endpoints is measured differently because simultaneity itself differs between the two frames. At modest speeds, the contraction is negligible, but near light speed it becomes dramatic. A destination that lies 10 light years away in Earth's frame might be separated by only a few traveler-measured light years if the spacecraft moves fast enough. This allows the crew to complete the journey in far less than 10 years, according to their own clocks. Even though Earth observers still see the trip taking more than 10 years once acceleration and travel are considered. The effect is reciprocal during steady relative motion. The travelers measure the distance ahead as contracted, while Earth observers measure the moving spacecraft as shortened along its direction of travel. There is no contradiction because each measurement depends on determining both ends at the same time, and the two frames do not share the same distant, same time. Cosmic ray particles demonstrate this relationship naturally. From Earth's perspective, their internal processes can be slowed by time dilation. From the particle's frame, the thickness of the atmosphere is contracted, allowing the ground to arrive sooner. These are not competing explanations, but two views of the same space-time geometry. Length contraction, therefore, does not provide a shortcut that beats light or makes the galaxy objectively smaller for everyone. It changes how much distance belongs to the traveler's route. A sufficiently advanced ship could cross enormous Earth-measured separations within a human lifetime on board, though the energy, acceleration, collisions, and radiation involved would remain severe obstacles. The stars would not truly lean toward you in some universal space, yet your own measurement of the gulf would shrink, revealing that distance is not a rigid property waiting unchanged between two places. It depends quietly and profoundly on how you move through the universe that contains them. One traveler can return younger than the person who stayed behind. When two people meet again after separating, their faces may reveal that the universe has given them different amounts of time. This is the heart of the famous twin paradox. One traveler leaves Earth in a high-speed spacecraft, turns around near a distant destination, and eventually returns to find that the person who remained behind has aged more. The result is not caused by a faulty clock or by the traveler somehow feeling time slow down. Every heartbeat, thought, meal, and mechanical process aboard the ship unfolds normally. The difference appears only when the two paths reunite, and their clocks can be compared side by side. At first, the situation may seem perfectly symmetrical. From the spacecraft, Earth is moving away. From Earth, the spacecraft is moving away. Why should either person age less? The answer lies in the complete shape of their journeys. The Earthbound observer remains approximately within one continuous frame, while the traveler must change direction to return, switching from a frame moving away from Earth to one moving toward it. That change breaks the apparent symmetry. In relativity, elapsed time depends on the route followed through space-time, much as the length of a trail depends on which path you take between two locations. Two travelers can leave the same event, follow different routes, and arrive at the same later event having accumulated different amounts of personal time. Acceleration is important because it allows the reunion, but the age difference is not simply a punishment for feeling a force. Even carefully designed journeys with different patterns of acceleration produce the same final comparison when their overall space-time paths are equivalent. This is not merely a thought experiment. Atomic clocks flown on aircraft and carried by satellites accumulate tiny differences that agree with relativity, although gravity also affects those clocks and must be included. For human travelers, the effect would become dramatic only at enormous speeds or in intense gravitational environments. A crew might experience a few years while decades pass on Earth, returning not to the world they left, but to a later generation that has been waiting far longer. Relativistic travel therefore contains a quiet emotional cost. It can shorten the traveler's journey without shortening the absence endured by everyone else. You may cross the stars within your own lifetime, yet the people who watched you leave could grow old before you return. Time is not a single river carrying everyone forward together. It is something each person gathers along a path, and reunion is the moment the universe finally reveals how unequal those paths have been. Two observers can disagree about which distant event happened first. Far apart in space, two events can trade places in time without either observer being mistaken. Imagine a research station near one star, firing a brief laser pulse while, many light years away, another station activates a powerful transmitter. An observer moving with the first station may calculate that the laser was fired before the distant transmitter switched on. Another observer, traveling rapidly in the opposite direction, may calculate that the transmitter activated first. A third might find that the two events occurred simultaneously. This does not mean time is chaotic, or that records can be rewritten at will. The reversal is possible only when the events are separated so widely that no signal traveling at or below light speed could pass from one to the other before both had occurred. Such events are called space-like separated because neither can influence the other. Nature does not require every observer to agree on their order. Each observer defines distant timing using clocks synchronized throughout their own state of motion. And different moving systems divide space-time into sets of simultaneous moments differently. The disagreement is therefore built into how distant time is measured, not caused by slow communication or careless calculation. Causally connected events remain protected. If one station sends a signal that later triggers an explosion at the other, every observer will agree that the transmission came before the explosion, even if they assign different amounts of time between them. No one can reverse the order of a cause and an effect linked by a physical signal. Only events lying outside one another's causal reach can exchange their apparent positions in time. This distinction matters because it removes the idea of a universal chronological list containing every event in the cosmos. The universe preserves local histories and causal chains, but it does not provide one absolute answer to the question of which unrelated event, separated by an enormous distance, happened first. Human intuition resists this because your daily life occurs at low speeds and over short distances, where the disagreement is too small to notice. You naturally imagine time as a hidden numbering system stamped identically across space. Relativity replaces that picture with something more subtle. Distant order depends partly on the observer's motion, while causal order remains firm. Reality allows disagreement where no consequence is at stake, yet becomes strict wherever one event can physically produce another. Perhaps time is not losing its structure here. Perhaps you are discovering that its deepest structure was never meant to resemble the single shared timeline your mind finds easiest to imagine. Every observer measures the same vacuum speed of light. The strangest agreement in physics is reached by observers who disagree about almost everything else. They may assign different lengths to the same moving spacecraft, record different durations between the same pair of events, and use clocks that do not agree about distance simultaneity. Yet when each carefully measures a pulse of light traveling through vacuum, every unaccelerated observer obtains the same speed. Before relativity, many scientists expected light to behave like sound. Sound moves through air, so its measured speed changes when you move relative to the air. It seemed natural to imagine that light traveled through an invisible substance called the luminiferous ether, giving the universe a preferred state of rest. Earth's motion through this ether should then have produced an ether wind, making light appear slightly faster in one direction and slower in another. Experiments designed to detect that difference, most famously the Michelson-Morley experiment, found no expected variation. Later measurements became vastly more precise, but the same principle survived. No local experiment reveals a preferred inertial frame through the vacuum speed of light. Einstein took this result seriously and rebuilt the concepts of space and time around it. The constancy does not mean every observer uses identical rulers and clocks. It means their measurements of distance and duration transform together so that the ratio obtained for light remains unchanged. A moving observer's clock's synchronization procedure and measured lengths differ from those of another observer in exactly the coordinated way required. The source cannot add its own motion to the beam either. Light emitted from a moving spacecraft does not travel at the usual speed, plus the spacecraft's speed, as a thrown ball might. The motion of the source changes the light's frequency, energy, and direction, as measured by others, but not its local vacuum speed. This statement must be kept local and precise. In curved spacetime, distant coordinate descriptions can assign unusual apparent speeds to light, and inside materials its effective propagation is reduced by interactions with matter. But any freely falling observer measuring a nearby light ray in vacuum obtains the same fundamental value. That shared result is not merely a curious property of illumination, it is the conversion factor linking space and time within spacetime itself. The reason different observers can disagree consistently without physical law falling apart. Light does not adapt its speed to satisfy every witness. Instead, every witness discovers that their own measurements of space and time were never as absolute as they seemed. Light appears slower in matter without changing its fundamental vacuum speed. The instant a beam enters, glass, water, or crystal, it seems to surrender part of its impossible speed, but the light has not forgotten the rule it follows in empty space. Inside matter, an electromagnetic wave interacts with the charged particles bound within atoms, especially electrons, causing them to respond to the passing electric field and generate their own tiny electromagnetic contributions. These responses combine with the original wave, producing a new overall pattern that advances through the material more slowly than light would cross the same distance in vacuum. It is often explained by saying photons are repeatedly absorbed and re-emitted, but that picture can be misleading for ordinary transparent materials, because the process is better understood as a coherent interaction between the traveling field and the material's atoms. Between interactions, light does not cruise through empty gaps at some reduced personal speed. Instead, the combined wave formed inside the medium progresses, with an effective velocity determined by how strongly the material responds. This is why light travels more slowly through diamond than through air, and why it changes direction when entering water at an angle. One side of the wavefront enters the slower material first and is delayed before the other side, rotating the direction of travel in a process called refraction. The fundamental vacuum speed remains untouched, because it describes how light propagates locally when no material is present to influence it. Once the beam exits the material and returns to vacuum, it resumes that universal speed without needing to accelerate as a car would. Different kinds of speed can also describe a wave, the motion of individual crests, the progress of a pulse, and the transfer of usable information do not always behave identically in unusual materials, which is why dramatic laboratory claims that light has been stopped or made superluminal require careful interpretation. What slows in ordinary glass is the effective advance of the signal through an interacting medium, not the fundamental causal limit of nature. The glass does not weaken light's deepest rule. It briefly makes the wave share its journey with matter, reminding you that motion through the universe depends not only on what is traveling, but also on what the traveler must continually disturb along the way. Different colors travel through glass at slightly different effective speeds. White light enters a piece of glass as one apparently unified beam, yet inside the material, its colors begin to lose step with one another. Red, green, blue, and every shade between them correspond to different frequencies, and the electrons within glass do not respond equally to all of those frequencies. The material's charged particles shift slightly when the passing electromagnetic field pushes them, but the timing and strength of that response depend on how closely the light's frequency relates to the natural ways the atoms and molecules can oscillate. Because each color interacts differently, each develops a slightly different effective speed through the glass. This phenomenon is called dispersion. In most ordinary transparent glass, shorter visible wavelengths such as blue and violet are delayed more strongly than longer wavelengths such as red, so blue light usually bends more sharply when it enters or leaves the material. A prism turns this small difference into something visible. The first surface separates the colors slightly, and the second surface increases that separation, spreading white light into a spectrum that reveals colors already present in the beam. The prism does not manufacture those colors or dye the light as it passes. It sorts wavelengths that were traveling together by giving each one a different path. This difference also creates practical problems. In a simple camera lens, colors may focus at slightly different distances, producing colored fringes around sharp edges in an effect called chromatic aberration. Lens makers reduce it by combining carefully chosen types of glass whose dispersions partly cancel. Optical fibers must also manage dispersion because different wavelengths or parts of a pulse can arrive at slightly different times, causing a sharp signal to spread and limiting how much information can be transmitted over long distances without correction. The details depend on the glass composition and the wavelength range. Near strong atomic resonances, the behavior can become far more complicated than the simple rule that blue is slower than red. Still, the basic lesson remains clear. Transparency does not mean passivity. A clear material may look as though it does nothing to light, yet at the atomic level it is answering every color in a slightly different rhythm. The spectrum emerging from glass is therefore a record of those hidden responses, showing that what appeared to be one beam was always a crowd of wavelengths waiting for matter to reveal their differences. Rainbow exists because matter delays each color differently. Chum. Rainbow is not a colored object hanging at a fixed location in the sky. It is a precise optical relationship created between sunlight, countless water droplets, and the position of your eyes. When sunlight enters a nearly spherical raindrop, it slows and bends, but each wavelength bends by a slightly different amount because liquid water delays different colors unequally. The separated light then travels through the droplet, reflects from its inner rear surface, and bends once more as it exits. After this sequence of refraction, internal reflection, and refraction again, the strongest outgoing rays leave at color-dependent angles. Red typically appears on the outer edge of the primary bow because it is deflected less, while violet appears nearer the inner edge because it is deflected more. Millions of droplets send light in many directions, but only those lying at the correct angle relative to the sun, and your eyes contribute to the rainbow you see. This is why the sun must be behind you and the bow appears in the opposite part of the sky. It is also why two people standing apart do not see light from exactly the same droplets, Each observer receives a personal rainbow assembled from a different set of water spheres, even though the bows appear to occupy the same distant region. From the ground, Earth's horizon usually hides the lower portion, leaving an arc, but from an aircraft or high viewpoint, a full circular rainbow may become visible. The dark band, sometimes seen outside the primary bow, known as Alexander's band, appears because fewer rays leave droplets at those intermediate angles. A fainter secondary rainbow can form when light reflects twice inside each droplet. This extra reflection reverses the color order and sends out less light, making the second bow dimmer. The familiar 7 named colors are also a human simplification, because the spectrum changes continuously without sharp natural borders. A rainbow therefore combines atomic response, droplet geometry, sunlight, and perception into one temporary structure. You cannot walk beneath it or reach its end, because moving changes the droplets and angles that create it for you. Its beauty comes from something more exact than decoration. Every color arrives along a path selected by the physical properties of water, turning a passing storm into a visible map of how matter separates light. Diamond bends light so strongly because of how its electrons respond. A diamond begins to sparkle long before light reaches the polished surface you can see, because its tightly arranged carbon atoms force the passing electromagnetic wave into an unusually strong interaction with matter. Diamond has a refractive index of about 2.42 in visible light, far higher than water or ordinary glass, which means light changes direction sharply when it crosses between air and the crystal. The reason is not that photons crash into carbon atoms like balls striking obstacles. As the electric field of the light passes through the diamond, it slightly distorts the distribution of electrons bound within the crystal's covalent bonds. Those electrons respond by producing their own electromagnetic influence, and the combined response shifts the timing of the wave as it moves through the material. Diamond's dense, highly ordered atomic lattice and electronic structure make this response especially strong, creating the large refractive index for which the gemstone is famous. But a rough diamond does not automatically produce the brilliance seen in jewelry. Its shape must be engineered. Because light bends so strongly at a diamond's surface, there is only a narrow range of angles through which it can easily escape from inside. At many other angles, the light is reflected back into the stone through total internal reflection. A skilled cut positions the facets so that incoming light repeatedly changes direction within the diamond and is redirected toward the observer instead of leaking through the bottom. If the stone is cut too shallow, light escapes beneath it. If it is cut too deep, much of the light leaves through the sides, and the diamond appears darker despite containing the same carbon. The colored flashes known as fire arise because different wavelengths are bent by slightly different amounts, but the intense white brightness called brilliance depends largely on how efficiently the cut returns light to your eyes. This is why 2 diamonds made from nearly identical material can look dramatically different. Their beauty is not stored inside them like a substance. It emerges from a partnership between electrons, crystal structure, geometry, illumination, and the position of the observer. What appears to be a tiny object producing its own inner light is actually guiding light through a carefully designed labyrinth, revealing that brilliance is sometimes not the creation of more light, but the art of preventing existing light from escaping in the wrong direction. Scientists have slowed light to the speed of a moving bicycle. Inside a cloud of atoms cooled to a fraction above absolute zero, scientists once reduced the forward progress of a light pulse to about 17 meters per second, a speed a fast cyclist could match. The experiment did not weaken the universal speed limit or make an isolated photon crawl through empty space. Instead, researchers created an extraordinary state of matter called a Bose-Einstein condensate, in which many ultra-cold sodium atoms behaved collectively rather than as an ordinary warm gas. Normally, a light pulse tuned to a strong atomic transition would be absorbed by such atoms and disappear. The scientists prevented this by shining a second beam, called a control laser through the cloud. That laser rearranged the quantum response of the atoms so that two possible absorption processes cancelled one another, opening a narrow window in which the pulse could pass without being absorbed. This phenomenon is known as electromagnetically induced transparency. Yet transparency was only part of the effect. Near that narrow window, the optical properties of the cloud changed extremely rapidly with frequency, causing the group velocity, the speed at which the pulse envelope and its usable information moved, to fall from hundreds of millions of meters per second to only 17. As the front of the pulse entered the condensate and slowed, the back continued arriving from outside at its ordinary vacuum speed, dramatically compressing the pulse until it could fit inside the tiny atomic cloud. During this passage, the excitation was no longer purely light. It became a hybrid of the electromagnetic field and a coordinated pattern within the atoms, sometimes described as a light-matter quasi-particle. The atoms carried more of the excitation as the control laser was weakened, making the pulse advance more slowly. This is why saying that individual photons simply traveled through the condensate like bicycles is an imperfect picture. The measured pulse behaved slowly because its information was being continually shared with the collective atomic state. When it emerged from the far side, that information returned to an ordinary traveling light pulse and continued through vacuum at the usual speed. The achievement did not prove that nature's ultimate limit could be reduced. It demonstrated something subtler. The apparent motion of light can be controlled by changing how matter temporarily carries it. In an environment colder than almost anywhere in the natural universe, light ceased to look like an untouchable cosmic messenger and became something scientists could compress, delay, and guide almost slowly enough to watch cross a room. Light can be temporarily stored inside matter and released later. A pulse of light can enter a cloud of atoms, vanish completely from view, and return later carrying the shape and timing of the original message. Yet the photons are not sitting motionless inside the material, like objects locked in a transparent container. In light storage experiments, a control laser first prepares an atomic medium so that an incoming pulse can enter through electromagnetically induced transparency. While the control beam remains active, the optical pulse and a collective atomic excitation exist as two parts of one shared state. The pulse's electric field carries some of the information, while a delicate pattern of quantum coherence forms among the atoms, preserving relationships such as phase, amplitude, and timing. As the control laser is gradually switched off, the light component shrinks until the traveling pulse disappears, while its information is mapped into that collective atomic pattern, often called a spin wave. At this stage, no ordinary beam is moving through the medium. The energy and information that previously belonged to the optical field are encoded across many atoms rather than stored in one atom or one stationary photon. When the control laser is switched on again, the process runs in reverse. The synchronized atoms collectively generate a new optical field, reconstructing a pulse that travels out of the material with properties inherited from the pulse that entered earlier. The retrieved light is not necessarily made from the exact same individual photons, because photons are indistinguishable excitations and can be absorbed and recreated. What matters is that the optical state, the organized information carried by the original light, has survived the interval. Storage cannot continue perfectly forever. Atomic motion, collisions, stray magnetic fields, temperature changes, and environmental noise gradually destroy the coherence, causing the release pulse to weaken or lose fidelity. Different systems therefore trade storage time against bandwidth, efficiency, and the ability to preserve fragile quantum states. Researchers have demonstrated optical memories in cold atomic gases, warm vapors, crystals, and solid-state devices, with the long-term aim of synchronizing photons, connecting distant quantum processors, and building quantum networks in which information can wait instead of being measured or lost. Ordinary electronic memory converts light into electrical signals before storing it. But a quantum memory seeks to preserve features that classical recording cannot fully copy. including superposition and entanglement. The deeper achievement is therefore not that scientists imprisoned a beam. They learned how to let light surrender its traveling form without surrendering its identity, leaving a silent arrangement inside matter that can later remember how to shine. Some wave patterns can move faster than light without carrying information. Not everything that appears to race across space is actually traveling from one place to the next. A wave pattern can sometimes shift faster than light because the pattern is not a material object and may not represent the motion of energy, information, or any individual part of the wave. Imagine several waves overlapping on the surface of water. Their crests can combine to create a bright-looking ridge that seems to move rapidly, even though the water itself only rises and falls locally. Light and other electromagnetic waves can behave in a similar way. The repeating crests of a smooth wave have what physicists call a phase velocity, and under certain conditions, this mathematical pattern can exceed the speed of light. In specially designed materials, even the peak of a pulse may appear to move faster than light, or emerge from the far side earlier than expected, because the material reshapes the pulse by weakening some parts and strengthening others. The peak seen at the exit is not always the same physical piece of the pulse that entered. It may be reconstructed from the pulse's leading edge, making the result look as though something crossed the material impossibly quickly. But a completely new signal contains a first disturbance, a sudden change that could carry previously unknown information, and that leading boundary cannot be created at the destination before a causal influence reaches it. No warning, instruction, or secret message outruns the universal limit. This distinction between a moving pattern and a moving message is easy to miss because your eyes naturally follow recognizable shapes and assume that the same thing is traveling continuously. Yet nature can rearrange a pattern so that its apparent position jumps forward without transporting a physical object across the intervening distance. The faster-than-light motion is real as a description of the pattern, but it cannot be used to send information into a region that ordinary light has not had time to reach. The universe therefore permits appearances that cross its speed limit, while quietly protecting the deeper rule beneath them. A shape may race ahead, but knowledge cannot arrive before the physical process capable of carrying it. A laser spot can sweep across a distant surface faster than light. Aim a laser toward an extremely distant wall and rotate it quickly enough, and the glowing spot can sweep across that surface faster than light without any photon breaking the cosmic speed limit. The effect becomes possible because a tiny change in the direction of the laser corresponds to an enormous sideways distance when the target is far away. If a beam was swept across the moon, for example, a modest rotation of the source could make the illuminated point move across the lunar landscape at an apparent speed greater than light. At first, this seems to offer an easy way around relativity. Simply use the moving spot as a signal, but the spot is not a single object traveling over the surface. The photons illuminating one crater are not sliding sideways into the next crater. They were emitted earlier along one direction, while a later group of photons leaves Earth along a slightly different direction and strikes another location. Each bright point is created independently by light traveling directly from the laser to that part of the surface. The apparent motion exists only when you connect those separate impacts into one continuous path. Someone standing at the first illuminated location cannot place a message into the spot and send it along the surface to someone farther ahead, because no physical carrier moves between them. To alter what happens at the second location, information must return to the laser source or travel directly across the surface, and either route remains limited by the ordinary speed of communication. The geometry also creates unusual observational effects. Because photons from different parts of the sweep may have different distances to travel before reaching an observer, the spot can appear to accelerate, split, or even move in a direction different from the beam's actual rotation. Astronomers study related effects when flashes of light sweep through clouds of interstellar dust, creating apparent motions that seem superluminal, even though the dust and photons remain obedient to relativity. The laser spot is therefore a motion made from replacement rather than travel. One patch becomes dark while another lights up far away. It can cross a distant landscape faster than light only because there is no traveler making the crossing. The edge of a shadow can move faster than light without moving any object. Shadow can race across a distant world at an impossible speed, yet nothing dark is actually moving through space. Suppose a powerful light source shines toward a very large screen, while a small object near the source rotates or shifts. The object blocks different rays at different moments, and the boundary between illuminated and unilluminated regions may sweep across the screen extraordinarily quickly. If the screen is sufficiently distant, a small movement of the blocking object can shift the shadow edge across millions of kilometers, allowing its apparent sideways speed to exceed the speed of light. But darkness is not a substance being thrown from one location to another. A shadow is simply the absence of photons that would otherwise have arrived. Each point on the screen becomes dark when the particular ray aimed toward it is blocked at the source, and it becomes bright when that route is opened again. One location on the screen does not tell the neighboring location that the shadow is approaching. Both respond independently to different light paths originating elsewhere. This prevents the moving edge from carrying a controllable message along the surface faster than light. An observer standing under the first darkened point cannot modify the passing shadow in a way that instantly affects someone farther along its path, because there is no object at the edge to alter, capture, or redirect. Any useful change must be communicated through matter or radiation, which again obeys the causal limit. Shadows can also behave in ways solid objects cannot. Their boundaries may stretch, shrink, curve, merge, or appear in several places at once depending on the shape of the light source and the arrangement of the surfaces receiving it. During an eclipse, the moon's shadow moves across Earth because the geometry of the sun, moon, and rotating planet changes, but the visible darkness is continually recreated at new locations rather than transported like a giant black sheet. The lesson is subtle. Speed alone does not prove that something has traveled. Sometimes what moves is only a boundary between presence and absence, a line your mind follows even though the universe has sent nothing along it. Particles can outrun light inside water without outrunning light in vacuum. Deep inside a nuclear reactor, an electric blue glow appears where no blue lamp is burning, created by charged particles moving faster than light can move through the surrounding water. This does not mean the particles have defeated the universe's ultimate speed limit, because that limit refers to light traveling through a vacuum. Water changes how an electromagnetic wave propagates, reducing light's effective speed to roughly 3/4 of its vacuum value, while energetic electrons produced by radioactive processes can still move faster than this reduced speed without ever reaching the true vacuum limit. As one of these charged particles rushes through the water, its electric field disturbs nearby molecules, briefly polarizing them as their positive and negative charges shift slightly apart. When the molecules return toward their normal state, they release electromagnetic radiation. If the particle is moving slowly enough, these small emissions spread in a way that largely cancels and blends into the background. But once it outruns light's effective propagation through the medium, the disturbances cannot move ahead of it. They accumulate into a coherent cone of radiation, much as pressure waves gather into a sonic boom when an aircraft exceeds the speed of sound. This is Cherenkov radiation, named after Pavel Cherenkov, whose experimental work helped reveal the phenomenon. Its familiar blue color is not caused by the water itself being blue or by nuclear fuel glowing from heat. The emission is stronger at shorter visible wavelengths, giving the combined light its characteristic blue-violet appearance, though some ultraviolet radiation is also produced, and the exact observed color can be affected by the material and the sensitivity of the eye or detector. The angle of the light cone contains information about the particle's speed, allowing Cherenkov detectors to identify and study fast-charged particles created in accelerators, cosmic ray showers, and neutrino interactions. A neutrino itself carries no electric charge and does not directly create the glow, but when it collides with matter, it can produce a charged particle that does. By recording the faint rings of light on the walls of enormous water-filled detectors, scientists can reconstruct the direction and energy of an event that might have begun inside the Sun, Earth's atmosphere, or a distant exploding star. The blue light is therefore more than a beautiful side effect of radiation. It is the optical footprint of a particle crossing a material faster than that material can transmit light, leaving behind a luminous shockwave while remaining safely beneath the deeper speed boundary that empty space never allows it to cross. Some cosmic jets look faster than light because of a relativistic illusion. Across the center of a distant galaxy, a bright knot of plasma can appear to travel several times faster than light. Yet the illusion is created precisely because the material is moving just below light speed and almost directly toward you. Relativistic jets are narrow streams of energetic matter launched from regions around compact objects, such as black holes, often extending for thousands of light years and shining strongly at radio, optical, X-ray or gamma-ray wavelengths. Astronomers do not watch a single blob complete its journey in real time. They compare images taken at different dates and measure how far a recognizable bright feature seems to have shifted across the sky. The strange result arises from a combination of extreme speed, viewing angle, and the travel time of the light carrying each image. Imagine a knot in the jet emitting one flash, then moving a great distance partly toward Earth before emitting another. The second flash begins its journey from a location closer to us, so it has less distance to cross. Although the emissions may have occurred months or years apart near the jet, their arrival times at Earth can be separated by a much shorter interval. Meanwhile, the knot has also moved sideways across our view. Dividing that apparent sideways distance by the compressed arrival time interval can produce a calculated speed greater than light. Nothing actually crosses the local space between two neighboring points faster than a light beam. The measured superluminal value belongs to the projection of the motion onto the sky, not to the true speed of the plasma. The same geometry also makes the approaching jet look unusually bright. Radiation emitted forward by material moving near light speed becomes concentrated into a narrow direction, an effect called relativistic beaming, while a jet traveling away from Earth may appear faint or even become difficult to detect. This is why some active galaxies seem to display one brilliant jet despite likely producing opposing flows. Apparent superluminal motion is valuable rather than embarrassing, because astronomers can combine the observed motion, brightness changes, and viewing geometry to estimate how fast the material is truly traveling and how closely the jet points toward Earth. Features in some jets have appeared to move many times faster than light, offering powerful evidence that matter near black holes is being accelerated to speeds extraordinarily close to the cosmic limit. The sky is not showing you a broken law. It is showing you how easily distance and timing can disguise motion when an object nearly keeps pace with the light, announcing where it has been. Quantum tunneling can appear superluminal without sending a faster-than-light message, i.e., quantum particle can emerge from the far side of a barrier sooner than a simple light speed crossing time seems to allow. But the result does not give you a hidden tunnel for sending messages into the past. In classical physics, a particle without enough energy to cross a barrier should turn back, like a ball rolling toward a hill it cannot climb. Quantum mechanics describes the particle through a spread-out wave of possible outcomes, and part of that wave can extend into and through the forbidden region. This creates a non-zero probability that a measurement will find the particle beyond the barrier, even though classical motion would never have carried it there. The difficult question is how long tunneling takes, because a quantum particle does not follow one visible trajectory through the barrier with a tiny clock attached to it. Physicists use several definitions of tunneling time, and those definitions do not always produce the same intuitive picture. In the Hartmann effect, for example, the measured delay associated with the peak of a transmitted wave packet can stop increasing normally as a barrier becomes thicker. Dividing the barrier's width by that delay can suggest an effective speed greater than light, and experiments with photons have observed transmitted peaks appearing earlier than a vacuum speed comparison pulse would predict. Yet the barrier strongly reshapes the incoming wave packet. It preferentially transmits certain components, suppresses others, and can rebuild the outgoing peak from information already present in the early leading portion of the original packet. The peak that emerges is therefore not a small object that secretly traveled intact through the barrier at an impossible speed. It is a reconstructed feature of a distorted and greatly weakened quantum wave. To send a genuine message, you would need to introduce a new controllable change that was not already contained in the pulse's leading edge. That first new information cannot be detected beyond the barrier before an ordinary causal signal could arrive. Tunneling is also probabilistic. Most particles may be reflected, and thicker barriers make successful transmission increasingly rare. Research analyzing relativistic tunneling has shown that the apparently superluminal peak or effective traversal time cannot be turned into reliable faster-than-light transport of particles or information. The effect remains scientifically important because it exposes how poorly everyday words such as path, arrival, and duration fit the quantum world. Something measurable can appear on the far side with timing that challenges classical intuition. Yet causality survives because the appearance of a wave peak is not the same as the arrival of a new message. Quantum tunneling does not open a door through the universal speed limit. It reveals that in quantum mechanics, even deciding what it means to pass through a door is more subtle than watching a traveler enter one side and emerge from the other. Entangled particles cannot be used to communicate faster than light. Entanglement seems to offer the perfect cosmic telegraph. Separate two linked particles by 1,000,000 kilometers measure one, and the other immediately produces a correlated result. But the message you hope to send disappears inside quantum randomness. When two particles are prepared in an entangled state, their measurable properties cannot be described as two independent sets of instructions. If you and a distant partner each measure one particle, your results can display correlations stronger than any ordinary shared plan could reproduce. Yet every result you see locally is unpredictable. You cannot choose whether your detector records one outcome or the other, so you cannot use the particle to encode a deliberate 0, 1, yes, or no. Your distant partner also sees a random sequence, and nothing in that sequence reveals whether you measured your particle, which setting you selected, or whether you touched your equipment at all. The remarkable pattern becomes visible only after both sides compare their records through an ordinary communication channel. They might discover that measurements made in matching ways are strongly related, but that comparison cannot occur faster than a conventional signal can cross the distance between them. This is the essence of the no-signaling principle. Quantum theory permits non-local correlations without providing a controllable superluminal message. Even quantum teleportation does not evade the restriction. Entanglement helps transfer an unknown quantum state, but the receiver cannot reconstruct that state until additional classical information arrives by normal means. The common image of one measurement physically commanding the distant particle is therefore dangerously incomplete. Quantum theory predicts the joint pattern connecting both experiments, but it does not supply a switch with which one observer can manipulate the other observer's local statistics. Bell experiments have shown that the correlations cannot be explained by simple local hidden instructions carried from the source, making entanglement genuinely stranger than classical coordination, but stranger than local classical. Physics does not mean usable as an instant. Telephone. Nature allows two distant laboratories to share a relationship that becomes undeniable when their histories are brought together, while refusing to let either laboratory exploit that relationship alone. Entanglement does not send a secret message through space. It creates a structure whose meaning exists only in comparison. The universe seems willing to connect outcomes more deeply than distance suggests, yet it keeps the connection hidden behind randomness until slower communication allows the observers to meet their evidence in the same story. Photons' behavior can be calculated by considering every possible path. To predict where a photon will arrive, quantum physics does something that sounds almost absurd. It allows every conceivable route between departure and detection to contribute to the answer. Richard Feynman's path integral approach does not begin by assigning the photon one secret trajectory that scientists simply fail to observe. Instead, the calculation associates a quantum amplitude with a vast collection of possible histories: direct paths, curved paths, long detours, reflections, and routes that would look completely unreasonable in ordinary life. These contributions are not added like ordinary probabilities. Each carries a phase, something like the position of a hand on a rapidly turning clock, so different alternatives can reinforce one another or cancel one another almost completely. Paths whose phases vary wildly tend to erase one another when combined. Near the route predicted by classical optics, however, neighboring alternatives often possess similar phases and reinforce one another, making the familiar path overwhelmingly important at large scales. This is one reason light usually appears to take an orderly route, even though the deeper calculation includes far more possibilities. The method can explain why reflection follows a precise angle and why a beam bends when crossing between materials. The observed route emerges from the combined contribution of alternatives rather than from a photon examining the scene and consciously selecting the quickest road. It is important not to turn the mathematics into a misleading movie. Saying that the photon tries every path is useful language, but the theory does not require imagining a tiny glowing ball splitting into countless classical copies that literally tour the universe. What is distributed among the alternatives is the quantum amplitude used to predict the outcome. Only when an interaction produces a recorded event do you find one localized result, such as a flash in a detector. Before that event, the theory describes a field of possible histories whose phases determine which outcomes are likely. The same framework grew into one of the central tools of modern quantum theory because it can describe far more than a ray of light, including particles, fields, and interactions. It also reveals how the orderly world of everyday physics can emerge from quantum possibility. Most strange routes do not vanish because nature forbids them individually, but because their contributions neutralize one another. What remains visible is the small family of alternatives able to cooperate. The photon's ordinary-looking journey may therefore be less like a single road chosen in advance and more like the surviving note produced after an unimaginable orchestra of possibilities has cancelled nearly all of its own sound. Single photon can interfere with its own possible routes. Send photons toward two open paths so faintly that only one photon is traveling through the apparatus at a time, and the detector will first appear to receive nothing more than isolated, unpredictable points. One photon arrives here, another there, each leaving a localized mark as though it were a tiny particle. But allow the experiment to continue, and those individual marks slowly accumulate into alternating regions of high and low probability, the unmistakable pattern of interference. The result cannot be explained by photons colliding with one another, because the source can be weakened enough that successive photons are separated in time. Each detection is singular, yet the distribution formed by many detections depends on both routes remaining available. In a double-slit setup, the quantum description assigns an amplitude to the alternative through one slit and another amplitude to the alternative through the other. Where those amplitudes reinforce, detections become more common. Where they cancel, detections become rare or disappear. A Mach-Zehnder interferometer makes the same idea especially clear. A beam splitter creates two possible routes, mirrors guide them apart, and a second beam splitter recombines them. By adjusting the relative path lengths, researchers can arrange for one detector to receive nearly every photon, while another remains almost dark. Block either route, and that careful interference vanishes, even though the photon would still have had an open path to a detector. The experiment does not prove that a miniature object physically divides into two ordinary halves. It shows that the alternatives must remain coherent, able to preserve a definite relationship until they recombine. If the apparatus records reliable witch path information, the interference disappears because the alternatives have become physically distinguishable. No conscious human needs to inspect the record. Interaction with a detector or environment is enough. This corrects one of the most persistent myths in popular quantum stories. Awareness is not a magical force forcing the photon to behave. What matters is whether the physical setup preserves or destroys the possibility of interference between alternatives. When the paths remain indistinguishable, the photon arrives as one indivisible detection, while behaving as though both possible routes shaped where that detection could occur. Wave and particle are therefore not two costumes the photon secretly chooses. The spreading probability and the localized arrival are parts of one quantum process. Each photon leaves only a dot, but the collection of dots reveals an invisible architecture that no individual impact displays. You never watch the photon interfere in the way you watch two water waves cross. You infer it from the places where single arrivals repeatedly appear, and from the silent bands where possibility has cancelled itself before matter ever records a flash. The expansion of space slowly drains energy from traveling light. A photon may begin its journey carrying fierce ultraviolet energy and arrive billions of years later as a faint infrared whisper, not because it grew tired, collided with hidden matter, or leaked energy into empty space, but because the universe expanded while it was traveling. As light crosses the cosmos, its wavelength is stretched along with the growing distance between widely separated regions. A longer wavelength means a lower frequency, and a lower frequency means that each photon is measured with less energy when it finally reaches an observer. This is cosmological redshift, one of the clearest signs that the universe has changed during the light's voyage. The effect differs from ordinary reddening caused by dust, which removes or scatters certain wavelengths, and it is not exactly the same as the Doppler shift produced by motion through a fixed space. Here, the geometry through which the wave travels evolves, steadily lengthening the wave itself. This raises an uncomfortable question. Where did the missing energy go? In a laboratory, you expect energy to move into another object, become heat, or reappear in some measurable form. But an expanding universe does not always provide a simple, universal energy total that remains fixed across all of space for all time. General relativity preserves energy locally. Small physical interactions still balance correctly. But in a changing cosmic geometry, global energy conservation cannot always be defined in the familiar way. The photon's lost energy is therefore not necessarily transferred into a hidden reservoir that could later be recovered. It reflects the fact that energy is measured relative to observers and to the space-time through which they move. This matters enormously in astronomy. Radiation released in the early universe has been stretched so severely that light once carrying far more energetic wavelengths now fills space as cold microwaves. Distant galaxies also appear redder and dimmer, partly because their photons arrive with reduced energy and at a slower rate, spreading the original emission over greater distances and longer observed intervals. The expansion of space does not stop light or remove it from existence. It changes what that light can deliver when it reaches you. A photon may preserve its identity across cosmic history while surrendering much of the energy it once carried, leaving you to confront a universe in which even energy, the quantity that seems most secure, depends on the evolving shape of the stage on which it is measured. The oldest light has traveled for billions of years from matter now, much farther away. The most ancient light reaching your instruments began its journey when the universe had no galaxies, no stars, and no planets. Yet the matter that released it is now vastly farther away than the number of years the light has traveled might suggest. This radiation, called the cosmic microwave background, was released about 380,000 years after the beginning of cosmic expansion, when the universe cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that transition, free electrons scattered light so frequently that space behaved like a glowing fog. Once atoms formed, photons could travel freely, and some of those photons have been crossing the universe ever since. Their journey has lasted roughly 13.8 billion years, so it may seem natural to imagine that their source is about 13.8 billion light-years away. But distance in an expanding universe is not that simple. While the photons traveled toward us, the space separating us from the regions that emitted them continued to grow. Those regions are now roughly 46 billion light-years away in what cosmologists call present-day comoving distance. The light did not cross that entire modern distance in a fixed universe. It began when the emitting matter was much closer, then continued forward while the cosmic scale changed around its path. This is why the observable universe has a radius far larger than the age of the universe expressed in light years. You are not seeing one physical shell that still sits where it was when the light departed. You are receiving radiation from every direction, released by matter that later evolved into distant cosmic structures, while new space accumulated between regions. The ancient photons have also been stretched by expansion from wavelengths associated with a hot young universe into the microwave band detected today at a temperature only a few degrees above absolute zero. Tiny variations in that background preserve a map of early density differences, the faint seeds from which galaxies and clusters eventually grew. When you study this oldest light, you are not looking at the first instant of existence, because the earlier universe was opaque to electromagnetic radiation. You are seeing the moment the cosmic fog cleared enough for light to escape. Its arrival teaches you that distance is not a frozen gap, and that a journey cannot always be understood by multiplying travel time by speed. The message has crossed billions of years, but its source has been carried far beyond the distance the message itself appears to describe, as though the universe continued opening the road behind the traveler long after the journey began. Every distant galaxy is seen at an earlier stage of its life. Somewhere in the sky, a galaxy may already have changed beyond recognition, while Earth continues to receive the image of its youth. Looking across space is unavoidably looking backward in time, because the light collected by a telescope left its source before it arrived here. A nearby galaxy may be seen as it existed millions of years ago, while the most remote galaxies appear as they were more than 13 billion years in the past. Astronomers call this interval look-back time, and it turns the visible universe into a layered record rather than a single present-day photograph. This allows scientists to study galaxy evolution directly across different eras. Nearby galaxies often display mature structures, older stellar populations, and heavy elements produced by many generations of stars. Farther back in cosmic history, galaxies tend to appear smaller, more irregular, richer in gas, and more intensely active in forming new stars. Their light may be dominated by young, hot stars and violent regions where matter is rapidly collapsing. By comparing large populations at different distances, astronomers can trace how repeated mergers assembled larger systems, how rotating disks became organized, how central black holes influenced surrounding gas, and how star formation rose to a peak several billion years after the universe began before gradually declining. Yet every distant image must be interpreted carefully. Faint galaxies are harder to detect. Dust can hide star formation, and expansion shifts important wavelengths into parts of the spectrum invisible to human eyes. Telescopes therefore observe radio, infrared, visible, ultraviolet, and X-ray light to reconstruct different aspects of a galaxy's past. Redshift helps estimate the cosmic era from which the light came, but astronomers combine it with models and distance measurements because the relationship depends on the universe's expansion history. You also cannot watch one distant galaxy age by waiting a human lifetime. The changes unfold over millions or billions of years. Instead, researchers compare many galaxies seen at different stages, much as a forest's life cycle might be inferred by observing seedlings, young trees, and ancient trunks at the same moment. The night sky is therefore not a census of what exists everywhere now. It is an archive assembled from unequal ages, with each direction revealing a different chapter of cosmic development. A galaxy's image may reach you long after its stars have moved, faded, or exploded. But that delay is precisely what makes astronomy possible. The universe cannot show you its entire present, so it gives you its history instead. A star can explode long before Earth receives the news. A star can die while still shining peacefully in your night sky, leaving Earth to admire a light that no longer has a living source. When a massive star exhausts the fuel supporting its core, gravity can overwhelm it in seconds, triggering a supernova powerful enough to forge heavy elements, launch material across space, and briefly outshine an entire galaxy. Yet the explosion does not become visible everywhere at once. If the star is 1,000 light-years away, Earth receives the event 1,000 years after it actually occurred near the star. During that interval, the final light emitted before the collapse continues arriving, so the star appears unchanged, even though its physical state has already been transformed into an expanding remnant, a neutron star, or perhaps a black hole. Betelgeuse offers a familiar example. It lies roughly several hundred light-years away, so the reddish star seen tonight is an image from centuries ago. It may explode tomorrow, or it may remain stable for tens of thousands of years. Current observations cannot honestly tell us that it has already died. What they reveal is only the latest information that has completed the journey to Earth. A supernova can also announce itself through more than visible light. Neutrinos escape the collapsing core rapidly and interact so weakly with matter that they may reach detectors before the first visible brightening escapes the surrounding stellar layers. Gravitational waves might carry another signature if the collapse is uneven enough, while different wavelengths of light emerge as the expanding debris heats, cools, and collides with nearby gas. Astronomers therefore do not receive one simple announcement, but a sequence of messages, each carrying information from a different layer of the disaster. By the time the first human telescope notices the explosion, the actual remnant may already have been evolving for centuries or millennia in its own region of space. This means the sky is filled with unresolved histories. Some stars you see are still burning much as they appear. Others may already have entered stages no observer on Earth will learn about within a lifetime. The uncertainty is not created by poor astronomy, but by distance itself. You never receive a live broadcast from the stars. You receive delayed evidence, carried across darkness after the event has surrendered all ability to change what it sent. A supernova seen tonight is not the moment a star dies, but the moment its ancient death finally becomes part of Earth's knowledge. The oldest light we can observe was released before the first stars existed. Long before the first star ignited, the entire universe glowed with a light that still surrounds you today, arriving from every direction as the oldest electromagnetic signal astronomy can directly observe. In the young universe, matter was not arranged into planets, galaxies, or even ordinary neutral atoms. Space was filled with a hot mixture of atomic nuclei, free electrons, and radiation, and photons could not travel far without colliding with charged particles. The cosmos was therefore opaque, more like the interior of a dense, glowing fog than the transparent darkness you see between stars now. As expansion continued, the universe cooled until electrons could remain attached to nuclei, forming mostly neutral hydrogen and helium. Once the free electrons became far less abundant, photons stopped scattering constantly and began traveling across space. That ancient release created the cosmic microwave background. It did not come from stars, because stars had not yet formed. It came from the fading thermal glow of the universe itself. The first stars appeared much later, perhaps around 100 million years after the beginning of cosmic expansion, when gravity had gathered enough primordial gas into dense regions capable of nuclear fusion. The microwave background therefore preserves a picture of an era before starlight, before planets, and before the chemical elements required for rocky worlds or biological life had been widely produced. Its tiny temperature differences are especially important. Some regions were slightly denser than others, and over immense spans of time, gravity amplified those small irregularities into the cosmic web of galaxies and clusters. In that sense, the oldest light does not show completed structures. It shows the faint beginnings from which structure could grow. Astronomers map its polarization and temperature with extraordinary precision to estimate the universe's age, composition, geometry, and early expansion history. Yet this radiation also marks a boundary. Electromagnetic telescopes cannot see through the earlier opaque plasma, no matter how powerful they become, because freely traveling light from that period does not survive as a direct image. To probe further back, scientists must search for other messengers, such as primordial gravitational waves or subtle imprints left on later matter. The oldest visible light is therefore both a revelation and a curtain. It shows you a universe with no stars and no familiar darkness, while concealing whatever happened before transparency began. Every galaxy you know emerged after that light was released, making the faint microwave glow not merely background radiation, but the surviving brightness of a cosmos that had not yet learned how to make a single sun. Cosmic horizon separates us from events we can never witness. There are events occurring in the universe whose light will travel forever without ever reaching Earth, not because something blocks the way, but because the future expansion of space prevents the journey from being completed. This boundary is called a cosmic event horizon, and it should not be confused with the edge of the observable universe. The observable boundary is determined by how far signals have managed to reach us since the universe became transparent. So it describes the past information currently available. The event horizon is about the future. It separates events that can still influence us someday from events whose signals, even if emitted now, will never arrive. Because cosmic expansion appears to be accelerating, sufficiently distant regions are being carried away in such a way that the remaining space between us and an incoming photon can grow faster than the photon reduces it. Locally, the light continues moving normally through every small patch of space, but the total route changes as the universe evolves. This creates a strange situation in which you may currently observe ancient light from a galaxy that has already crossed beyond our event horizon. The photons visible today began traveling when conditions were different, and the galaxy was more causally accessible. New light emitted there now, however, may never join our history. The horizon is not a glowing wall surrounding Earth, and nothing dramatic happens to a galaxy as it crosses. An observer living there would not feel removed from the universe or see a boundary pass overhead. Every observer has a horizon centered on their own location, defined by which future signals can reach them. Over extremely long timescales, galaxies outside our gravitationally bound neighborhood will appear increasingly redshifted, faint, and slow, until their signals become effectively undetectable. Future astronomers living in the merged remains of the local group may see a far emptier cosmos and have much less direct evidence that countless external galaxies ever existed. The horizon therefore limits more than travel. It limits future knowledge. There may be supernovae, civilizations, planetary births, and entire galactic histories that occur beyond it, without leaving any possible trace in our region. This does not make those events unreal. It means reality is larger than the collection of events that can ever become part of our evidence. Human thought often treats the universe as something that could eventually be surveyed if intelligence became patient and advanced enough. But a cosmic event horizon places a permanent boundary on that hope. Some mysteries are difficult because technology is young. Others are unreachable because space-time itself has removed every path by which an answer could arrive. Space expanded faster than light during the universe's earliest moments. Before the universe was even old enough to form atoms, a region smaller than anything you could meaningfully picture may have expanded into an enormous cosmic domain in a fraction of a second. This proposed episode is known as cosmic inflation, and it does not describe particles blasting through space faster than light. Instead, It describes space itself increasing its scale so rapidly that two locations could become separated faster than a light signal could cross the growing distance between them. Relativity forbids matter, energy, and usable information from locally overtaking light, but it does not require the distance between extremely remote points in an expanding geometry to grow below that limit. Inflation was introduced to explain several puzzling features of the observable universe. Regions now separated by immense distances have nearly the same temperature, even though ordinary expansion seems to leave too little time for them to exchange heat and become so uniform. Inflation suggests that these regions were once close enough to interact before being violently carried apart. It also helps explain why the universe appears geometrically close to flat, much as a tiny patch of an enormous curved surface can appear flat when enlarged beyond recognition. Perhaps most importantly, microscopic quantum fluctuations present during inflation may have been stretched to astronomical scales. Slight differences in density later gave gravity places to begin gathering matter, eventually helping form the cosmic web, galaxies, stars, and the environments from which planets emerged. Inflation is strongly supported by several broad observations, but its exact mechanism remains uncertain. Scientists do not yet know what field drove it, precisely how it began, or whether it occurred in the simplest way current models describe. When inflation ended, its stored energy may have transformed into a hot mixture of particles and radiation, beginning the more familiar, hot early universe. The idea, therefore, does not claim that the Big Bang was an explosion from one point into surrounding emptiness. Every region of space expanded, and there may never have been an external room into which it grew. What became enormous was not an object traveling across a background, but the background's own scale. The earliest universe may have created distance faster than light could bridge it, leaving behind a cosmos whose remarkable smoothness and tiny imperfections still preserve the faint signature of that brief, almost unimaginable expansion. The observable universe is larger than the distance light has traveled. The observable universe reaches far beyond 13.8 billion light-years. Even though light has had only about 13.8 billion years to travel since the early cosmos, the apparent contradiction disappears when you stop imagining photons crossing a universe whose size remained fixed during their journey. While ancient light moved toward the region that would become Earth, the space between large cosmic regions continued expanding. A photon could make progress toward us through every local part of its path, while the total distance separating its source from our eventual location changed around it. The most distant matter, whose ancient signals can now be observed, is therefore currently much farther away than a simple multiplication of travel time and light speed would suggest. In the standard cosmological picture, the present distance to the edge of the observable universe is roughly 46 billion light-years in every direction, giving the observable region a diameter of about 93 billion light-years. This does not mean the light traveled 46 billion light-years through a static arena. It began when the emitting matter was closer, crossed an evolving geometry, and arrived after the source region had been carried to a far greater present-day distance. Cosmologists distinguish several kinds of distance because one number cannot answer every question in an expanding universe. Light travel distance describes how long a signal has been journeying. Present proper distance describes how far away the source would be, now according to a chosen cosmic time. Other definitions are useful for comparing brightness, apparent size, and redshift. None is simply fake or correct. Each describes a different measurable relationship. The boundary of what you can observe is often called the particle horizon, marking the greatest distance from which any signal has had time to influence us since the early transparent universe. Beyond it may lie vastly more space, perhaps even an infinite amount, but its light has not reached Earth and may not yet have had any opportunity to become part of our evidence. The observable universe is therefore not necessarily the whole universe. It is the portion whose history has managed to arrive. Its enormous present size reveals that distance is not merely empty separation waiting between objects. It evolves with cosmic time, allowing the visible domain to become much larger than the path any single photon would have crossed in an unchanging world. The night sky is dark, partly because light has had only a finite time to reach us. Perfectly eternal universe filled uniformly with everlasting stars should leave no darkness between them. Every direction you looked would eventually end on a blazing stellar surface, making the whole sky shine with something approaching the brightness of a star. This puzzle is known as Olber's paradox, and the fact that night is mostly dark tells you something fundamental about cosmic history. The universe has not existed in its present transparent, star-filled condition forever. Stars formed only after an early period without them, and their light has had a finite amount of time to cross the enormous distances separating galaxies. When you look deeply into space, there eventually comes a point beyond which ordinary starlight has not had enough time to arrive. There is no infinite series of visible stellar shells contributing unlimited brightness to every patch of sky. Cosmic expansion deepens the darkness. Light traveling for billions of years is stretched toward longer wavelengths, reducing the energy delivered by each photon and slowing the rate at which those photons arrive. Radiation that once belonged to visible or ultraviolet light can be shifted into infrared or microwave wavelengths that human eyes cannot detect. Stars are also temporary rather than eternal. They ignite, consume fuel, evolve and die, while galaxies pass through eras of intense and weak star formation. Dust can absorb visible light, but dust alone cannot solve the paradox, because in an eternal universe it would eventually heat up and re-radiate the absorbed energy. The true explanation requires a universe with a finite observable history and changing conditions. The night is not perfectly black either. Earth's atmosphere produces a faint air glow. Sunlight scatters from interplanetary dust. Unresolved stars contribute background light, and the cosmos is filled with microwave radiation left from its early hot state. Your eyes simply detect only a narrow part of this wider glow. Darkness is therefore not evidence that space contains nothing. It is the visible consequence of limits, limited time, limited stellar lifetimes, expanding distances, and wavelengths stretched beyond sight. Each dark interval between stars is not merely an empty gap. It is a reminder that much of the universe is too young, too remote, too redshifted, or too faint to illuminate your eyes, allowing night to preserve the history of a cosmos that did not shine forever. A black hole traps light by reshaping every possible path into the future. A black hole does not capture light by reaching outward like an invisible hand. It traps light because, beyond a certain boundary, every direction that could lead into the future points deeper inside. Around an ordinary star, a flash can travel outward, sideways, or inward, depending on how it is aimed. Near a black hole, space-time becomes so strongly curved that these possible routes begin to tilt toward the center. The event horizon marks the place where the last outward-directed path merely remains on the boundary instead of escaping, while every future-directed path inside it leads towards smaller distances. A photon emitted inward falls deeper, but even a photon aimed directly outward cannot regain the exterior once it begins from inside the horizon. This is not because light slows below its normal local speed. Any nearby freely falling observer would still measure it moving normally past them. What changes is the shape of the available future. A useful picture is a river whose current grows stronger as it approaches a waterfall. Far upstream, a swimmer can move either with or against the flow. At the critical point, swimming outward only holds position, and beyond it, every effort still carries the swimmer toward the fall. The analogy is imperfect, but it captures why the horizon is not a solid shell that blocks light. There may be no material surface there at all. The trap is geometric. In relativity, light traces the straightest possible routes through curved space-time, and near a black hole those routes bend so severely that escape stops being one of the future possibilities. This also explains why a black hole can remain black even though nothing physically grabs the photon. Once the horizon has been crossed, Outward survives as a local spatial direction, but it no longer leads to the outside universe in the future. Escaping would require moving not merely faster through space, but outside the causal structure spacetime permits. The deepest strangeness of a black hole is therefore not that gravity defeats light in a contest of strength. It is that gravity changes the map on which every contest must occur, quietly removing the road called escape from all the roads that still lead forward. A falling object appears to freeze and fade near a black hole's horizon. Watch a clock fall toward a black hole from a safe distance, and its final seconds seem to stretch into an endless farewell. As the object approaches the event horizon, each pulse of light it sends outward must climb through increasingly severe gravitational curvature before reaching you. The pulses arrive farther apart, making the clock appear to run more slowly, while their wavelengths stretch toward red and then beyond visible light into infrared and radio frequencies. At the same time, the received energy falls and the image grows dimmer. In the coordinate system commonly used by a distant stationary observer, the object never appears to cross the horizon at any finite external time. Its motion seems to slow, then nearly freeze just above the boundary. But this does not mean a permanent photograph remains suspended there for eternity. The outgoing signals weaken dramatically, and after a relatively short observational period, they become too redshifted and too faint for any realistic telescope to detect. Light emitted later also struggles longer to escape, so the distant universe receives an increasingly delayed and impoverished record of the fall. The object may appear to become a dark, fading outline rather than a sharply frozen body. If the black hole is surrounded by a hot gas, that glare would make the final image even harder to isolate. The apparent freezing is therefore a statement about how information reaches the distant observer, not evidence that the object physically stops at the horizon. Different coordinate systems describe the crossing without this infinite delay, showing that the frozen picture is not a universal event every observer must agree upon. What remains physically meaningful is the sequence of signals you receive. Slower, redder, weaker, and progressively closer to silence. You never witness the exact crossing in the ordinary visual sense, because no final flash arrives announcing the horizon has now been passed. Instead, the object is gradually erased from your accessible view. A black hole hides in falling matter not by snapping the image off at one visible instant, but by stretching its final messages until time itself seems to dissolve them into darkness. The falling object crosses the horizon, normally from its own point of view. For the traveler falling into a sufficiently large black hole, the event horizon may pass without a flash, a collision, or any local sign that a famous boundary has just been crossed. The traveler's watch continues ticking normally, their thoughts remain continuous, and nearby objects still obey familiar local physics. They reach and cross the horizon after a finite amount of their own proper time, directly contradicting the distant impression that they remain forever outside. This difference is possible because the horizon is not a material surface located by a painted line in space. It is a global boundary defined by whether future signals can ever reach the distant exterior. A person crossing it cannot necessarily identify the exact moment using only a small laboratory around them, especially if the black hole is enormous and relatively quiet. Tidal forces provide the real physical danger, but their strength at the horizon depends strongly on the black hole's mass. Near a small black hole, the difference in gravity between the traveler's head and feet could tear them apart before or near the crossing. Near a supermassive black hole, the horizon can be so large that the local tidal forces there are initially mild, allowing the traveler to pass intact before stronger stretching develops deeper inside. Crossing still changes their future permanently. They may continue receiving light from the outside universe for a while, though that view would be distorted by motion, gravity, and the surrounding environment. They can also send signals outward before reaching the horizon, but every message emitted after crossing remains trapped. No engine can reverse the journey then, because all future-directed routes lead inward. The traveler does not see the whole future history of the universe instantly. despite a popular myth. The amount of outside time visible depends on the trajectory and black hole environment, and the journey to the interior remains finite. In the simplest non-rotating black hole model, the traveler eventually encounters a singularity where the known theory predicts its own breakdown. Rotating black holes have more complicated mathematical interiors, but realistic disturbances may make them violently unstable. The horizon itself, however, need not feel like the dramatic gate imagination expects. That may be its most unsettling quality. The irreversible moment can arrive quietly, with no alarm from nature, while the traveler's immediate world feels ordinary. Only afterward does the deeper truth become unavoidable. Every second still lies ahead, but none of those seconds contains a path home. Light can orbit a black hole before escaping or falling in. There is a narrow region around a black hole where a beam of light can circle the darkness as though it has forgotten whether to leave or fall. Around a simple, non-rotating black hole, this region is called the photon sphere, and it lies outside the event horizon. Here, spacetime is curved strongly enough for light to follow a circular route, but the orbit is dangerously unstable. A perfectly placed photon could circle the black hole, yet the smallest disturbance would decide its fate. Shift slightly outward and it may spiral away into space. Shift slightly inward and it will descend toward the horizon. Real light approaching from farther away can pass close to this region, loop around the black hole one or several times, and then escape toward a distant telescope. This does not usually create one clean glowing ring made of photons permanently orbiting in place. Instead, it produces a sequence of extremely thin, distorted images of whatever light source lies around or behind the black hole. Radiation from a glowing accretion disk may travel directly toward you, while other rays complete half an orbit, one orbit, or several orbits before arriving. Each additional loop creates another narrower and fainter image crowded close to the edge of the black hole's apparent shadow. In principle, those higher-order images carry information about the black hole's gravity and the structure of the material surrounding it, but resolving them is extraordinarily difficult because they are compressed into such a small region. A spinning black hole makes the geometry more complicated. Space-time is dragged around with the rotation, allowing light traveling with the spin and light traveling against it to follow different paths. The photon region is then no longer described by one simple spherical shell, yet the deeper lesson remains unchanged. Light does not orbit because gravity pulls on it as though photons were heavy stones tied to an invisible rope. It follows the available routes through curved space-time, and near a black hole some of those routes bend back upon themselves. The photon sphere is therefore not a safe celestial highway, but a razor-thin border of possibilities, where a change too small to see can separate escape from disappearance. A ray that reaches your telescope after circling the black hole may be showing you the same luminous material from an unexpected direction, carrying an image folded around darkness before finally being released. One galaxy can appear in several places because gravity splits its light. Of a single distant galaxy can arrive in your telescope as two images, four images, a curved arc, or a nearly perfect ring, making one object appear to occupy several places in the sky at once. The galaxy has not divided, and no copies of it are scattered through space. The multiplication occurs when a massive foreground object, often another galaxy or an entire galaxy cluster, lies between the source and Earth. Its gravity curves the surrounding space-time, so light leaving different parts of the background galaxy can follow several distinct routes around the foreground mass and still reach you. Your eyes and instruments normally assume that light has traveled along a straight line, so each arriving path is traced backward to a different apparent position. The result is strong gravitational lensing, one source reconstructed as multiple distorted images. When the source, lens, and observer are aligned with unusual precision, the light may be stretched into an Einstein ring. With less perfect alignment, the ring breaks into arcs or separate images arranged around the lensing mass. The shapes are not decorative accidents. Their curvature, spacing, and brightness depend on the distribution of mass in the foreground object, including matter that produces no light of its own. Astronomers can therefore use the distorted background galaxy as a probe, working backward from the lensing pattern to map invisible concentrations of dark matter inside clusters and galactic halos. Lensing can also magnify sources that would otherwise be too faint or distant to study, turning a massive cluster into a natural telescope created by spacetime itself. But the magnification is uneven. One part of a galaxy may be enlarged more than another, while some images are flipped, stretched, or compressed. So researchers must carefully reconstruct the original source rather than treating the brightest arc as a faithful photograph. In rare alignments, countless background galaxies can be warped around the same cluster, filling one image with repeated curves that reveal both the hidden mass in front and the ancient galaxies behind. To an uninformed observer, such a field might look crowded with unrelated objects. To a physicist, it is one scene viewed along multiple gravitational routes. The galaxy remains singular at its source, yet its light reaches you through several histories, forcing the sky to display different apparent locations for one distant reality. Gravity has not created additional galaxies. It has changed the directions from which the original galaxy is allowed to be seen. Gravity can delay light, even when its local speed never changes. Send a radar signal past the Sun toward another planet, and the echo will return slightly later than it would in a universe without the Sun's gravitational field, even though every nearby observer along the route still measures light moving at the usual vacuum speed. This extra travel time is called the Shapiro delay, and it reveals why saying that gravity slows light can be both useful and misleading. General relativity does not place light inside space as though it were crossing an ordinary flat map, while some invisible resistance holds it back. The Sun curves space-time itself, altering both the geometry of the route and the way clocks at different gravitational depths relate to one another. From Earth's coordinate description, a signal passing close to the Sun takes longer to complete its journey than a simple flat space calculation predicts. Part of that delay can be understood as the path being shaped by curved geometry, while part comes from the gravitational behavior of time. Yet if a freely falling observer near the ray measured the light over a sufficiently small region using a local clock and ruler, the result would still be the standard vacuum speed. There is no contradiction, because local speed and total travel time across an extended curved region are not the same measurement. The Shapiro effect was tested by transmitting radar waves toward planets such as Venus when their path passed near the Sun, and comparing the returning signal with the timing predicted by different theories of gravity. Later radio links with spacecraft allowed far more precise measurements. The delay is tiny by ordinary human standards, but modern navigation and planetary science cannot simply ignore such relativistic corrections when extreme accuracy is required. Similar delays occur near other massive bodies, growing stronger when light passes through deeper gravitational environments. A signal crossing the curved space-time around a galaxy cluster or compact star may therefore arrive later than another signal following a less strongly curved route, even if both rays move locally at the same fundamental speed throughout their journeys. This teaches you that knowing a traveler's speed is not enough to predict an arrival time when the road and the clocks used to measure it are part of the gravitational landscape. Light never needs to press an accelerator after leaving the Sun's influence, because it was never locally crawling. The delay belongs to the complete path through space-time, not to a tired photon moving too slowly. Gravity changes the meaning of distance and duration so subtly that the beam always appears locally faithful to its speed limit, while the universe quietly adds time to the journey. Light loses energy while climbing out of a gravitational field. A beam of light escaping from a massive world arrives above it, carrying less energy than it had when it began, even though no friction touched it and no hidden substance drained it along the way. This effect is called gravitational redshift, and it emerges because gravity changes how time passes at different locations. A clock deeper in a gravitational field runs more slowly relative to a clock farther away, so light emitted near the massive object is judged differently when it reaches an observer higher up. The photon is received with a lower frequency and a longer wavelength, shifting its light toward the red end of the spectrum. It is tempting to picture the photon spending energy like a stone thrown upward, but that analogy must be used carefully. Light does not gradually slow as it climbs. Every nearby observer still measures it traveling at the usual local vacuum speed. What changes is the energy assigned to the photon by observers whose clocks occupy different gravitational conditions. If the process is reversed and light falls deeper into a gravitational field, it is measured at a higher frequency and becomes gravitationally blue-shifted. This was tested on Earth in the Pound-Rebka experiment, which measured an extremely small frequency change over the height of a building using gamma rays. Modern atomic clocks can detect the same principle across differences in height small enough to exist within a laboratory, revealing that even the gravitational difference between the floor and a shelf changes the rate at which time accumulates. The effect must also be considered in satellite navigation, because clocks orbiting Earth experience gravity differently from clocks on the ground, around stars, white dwarfs, and other compact objects. Gravitational redshift becomes strong enough to shift recognizable spectral lines away from the wavelengths measured in laboratories. Astronomers can use this displacement to learn about the gravity near the place where the light was produced. Yet the energy has not simply vanished into a universal account that every observer would measure identically. Energy in relativity depends partly on the observer and on the geometry of spacetime, so observers at different gravitational heights can assign different energies to the same traveling photon while remaining physically consistent. The light arrives redder, not because it has grown old or weak in an ordinary mechanical sense, but because it has crossed between regions where time itself is measured differently. When you see gravitationally redshifted light, you are not merely seeing a changed color. You are seeing the imprint of unequal clocks written directly into radiation. Neutron star can stretch, escaping light into much redder wavelengths. Imagine compressing more mass than the sun contains into a sphere roughly the size of a city, then asking a photon to climb away from its surface. That is the environment surrounding a neutron star, where matter is packed so densely that a small amount would outweigh mountains, and gravity becomes strong enough to leave a dramatic signature on escaping light. Radiation produced in the star's hot surface layers may begin at one wavelength and arrive at Earth shifted noticeably toward the red. The effect can be tens of % for a typical neutron star, far stronger than the gravitational redshift produced by Earth or the Sun. If atoms in the star's atmosphere absorb light at particular, well-known frequencies, astronomers can compare those spectral features with the same atomic patterns measured in laboratories. The amount of displacement can reveal how compact the star is, how much mass has been squeezed inside a particular radius. This is especially valuable because neutron star interiors cannot be reproduced in ordinary laboratories. Their cores may contain superfluid neutrons, superconducting protons, exotic particles, or states of matter that remain uncertain. And each proposed interior changes the relationship between the star's mass and size. Gravitationally shifted light can therefore help test which descriptions of ultra-dense matter are realistic. The measurement is difficult, however, because neutron stars are not clean, quiet spheres. Their magnetic fields can be trillions of times stronger than Earth's, splitting and shifting atomic energy levels in ways that can imitate or complicate gravitational redshift. Their surfaces may rotate hundreds of times each second, producing additional wavelength changes from motion. Hotspots surrounding gas and uncertain atmospheric composition can further distort the spectrum. Scientists must separate all these effects before treating a red feature as a direct measurement of gravity. The star's intense curvature also bends escaping rays, allowing an observer to see more than half of its surface at once. Light emitted from regions that would normally lie beyond the visible edge can curve around the star and enter the telescope. changing the pulse shape as rotating hotspots pass through view. Neutron star astronomy therefore reads several relativistic effects together. Redshift reveals the depth of the gravitational field, light bending reveals the curvature around the surface, and pulse timing constrains rotation and geometry. The photon that finally reaches Earth may have traveled across the galaxy, but one of the most important changes in its history happened during the first moments of escape. Its stretched wavelength carries a quiet measurement of a place where matter has been pressed almost as far as it can go, without disappearing behind a black hole horizon. Black hole's shadow is larger than the event horizon creating it. The dark circle photographed around a black hole is not a direct picture of the event horizon, and the darkness you see is substantially larger than the hidden boundary that makes escape impossible. A black hole's shadow is an apparent region on the sky created by the capture of light and the extreme bending of rays passing nearby. Some photons aimed toward the black hole fall through the horizon, while others curve around it and escape toward the observer. Between those outcomes lies a narrow and unstable range of paths that can loop around the black hole before deciding whether to escape or vanish. Because gravity redirects light from behind and around the object, the set of captured directions covers a larger apparent area than the horizon itself. For a simple non-rotating black hole viewed from far away, the shadow's diameter is roughly 2.5 times the diameter of the event horizon. This does not mean the black hole has a larger physical surface than relativity predicts. It means the surrounding spacetime acts like a powerful lens, enlarging the dark silhouette produced by the region from which rays fail to return. The bright ring surrounding the shadow is also easy to misunderstand. Much of it comes from hot plasma in the accretion flow, whose light has been bent and concentrated around the apparent edge. The extremely thin theoretical photon ring, formed by rays that complete additional loops, is only part of the broader luminous structure and may be difficult to separate with present instruments. A spinning black hole changes the image further. Rotation drags spacetime around with it, shifting the paths of light and making the shadow slightly asymmetric depending on the black hole's spin, the viewing angle, and the motion of the glowing material. Yet even rapidly spinning black holes often retain a roughly circular shadow because gravity dominates the overall geometry. When the Event Horizon Telescope produced images of the black holes in Messier 87 and at the center of the Milky Way, it did not photograph a solid black sphere against empty space. It reconstructed radio emission from hot matter surrounding a central brightness depression shaped by gravitational lensing and photon capture. Measuring the size of that depression allows scientists to test whether the observed geometry agrees with general relativity and with independent estimates of the black hole's mass. The shadow is therefore not the horizon itself, but a magnified consequence of what the horizon does to nearby light. You are seeing absence enlarged by curvature, a dark shape drawn not at the exact location of the boundary, but across every direction from which space-time refuses to return an image. The photon sphere is a ring where light orbits on an unstable edge. There is a place outside a black hole where light can circle in perfect balance, yet that balance is so fragile that no ordinary beam can remain there for long. Around an ideal non-rotating black hole, this region is known as the photon sphere, a spherical zone rather than a solid ring or physical surface. Any photon following an exactly circular route there moves at its usual local speed, but the curvature of space-time continually redirects its path until it closes around the black hole. The orbit is unstable because even the smallest deviation grows rapidly. A photon displaced slightly outward can break free and escape, while one shifted slightly inward is drawn toward the event horizon. Unlike a planet circling a star, it cannot settle into a neighboring stable orbit after a disturbance. This instability is why the photon sphere should not be imagined as a permanent necklace of trapped light glowing around the black hole. Individual rays may pass near it, complete part of a circle or several loops, and then either escape or disappear, but a lasting collection would require impossible precision and would be disturbed by surrounding matter. Rotation complicates the picture further. Around a spinning black hole, space-time itself is dragged in the direction of the spin, so photons moving with the rotation can orbit differently from those moving against it. Instead of one simple photon sphere, physicists speak more carefully of a photon region containing a family of possible light paths. These paths influence the detailed outline of black hole images and help determine which directions appear dark to a distant observer. They also create a peculiar possibility. Light escaping after several circuits can carry delayed and highly distorted information from the same luminous source, producing nested image structures too narrow for most current telescopes to resolve clearly. The photon sphere is therefore not merely a dramatic ring near darkness. It is a boundary where geometry temporarily balances light on an unstable edge, demonstrating that an orbit can exist without matter, without a surface, and without safety. The light is never at rest, yet its route can become circular. It is never imprisoned permanently, yet one tiny change can decide whether the wider universe will ever receive it. Gravity allows telescopes to see objects hidden behind other objects. An object directly behind a galaxy cluster should be invisible, yet gravity can bend its light around the obstruction and deliver it to a telescope from directions the source never occupied in the sky. This makes a massive foreground object behave like a natural lens. Though unlike a glass lens, it has no polished surface and may be millions of light years wide. Light passing on different sides of the foreground mass follows curved routes through the distorted space-time around it, allowing radiation from a hidden background galaxy, star, or supernova to reach Earth even when the direct line of sight is blocked. The effect can reveal sources that would otherwise remain both concealed and too faint to detect. A cluster's gravity may magnify a remote galaxy by concentrating some of its light into stretched arcs, increasing its apparent brightness enough for astronomers to study structures formed when the universe was young. This magnification does not create extra light. It redistributes the light across the observer's sky, often enlarging the image while preserving surface brightness. The price is distortion. A magnified galaxy may appear curved, duplicated, or stretched so severely that researchers must mathematically reconstruct its original form. Gravitational lensing works across several scales. Entire clusters can reveal distant galaxies through strong lensing. Individual galaxies can slightly distort thousands of background sources through weak lensing, and a single foreground star can briefly brighten a hidden background star through microlensing. Microlensing usually produces no resolvable split image because the separation is too small, but the temporary brightening can reveal planets, dark stellar remnants, or other objects that emit little or no light. Lensing has even helped detect galaxies located behind dense foreground systems, and stars temporarily magnified inside extremely distant galaxies. The foreground object, therefore, does not merely block the view. Under the right alignment, its gravity opens alternative routes around itself. A telescope looking through such a lens is not seeing through matter in the ordinary sense. It is receiving light that has traveled around the obstruction along paths curved by mass. What appears hidden from a straight line may still remain visible to a universe where straight lines themselves are bent. Delays between gravitationally lensed images can help measure cosmic expansion. A distant quasar can flicker once and appear to repeat the same change days, months, or even years later, not because it erupted twice, but because different images of the same event traveled along unequal routes to Earth. When a foreground galaxy gravitationally lenses a variable background source, its light may arrive through several paths. One route may be geometrically longer, while another passes deeper through the foreground galaxy's gravitational field, where the structure of space-time adds further delay. The result is a set of images showing the same quasar at slightly different moments in its history. If the quasar brightens, fades, or changes color, astronomers can identify the matching pattern in each image and measure the time separating their arrivals. Those delays contain information about the scale of the universe. To interpret them, researchers construct a model of the lensing galaxy's mass, including its stars, dark matter, and surrounding environment. The observed image positions reveal how strongly the light was deflected, while the delay reveals how the geometry of the entire route relates to cosmic distances. Because those distances depend on the expansion rate, the system can be used to estimate how quickly the universe is expanding today. This method, known as time delay cosmography, is valuable because it does not rely on exactly the same chain of calibrations used by traditional distance ladder measurements. Lensed supernovae can serve a similar purpose when their changing brightness is observed in multiple images. The method is powerful but demanding. An incorrect model of the foreground mass can shift the inferred expansion rate, and small stars inside the lensing galaxy can microlens individual quasar images, altering their brightness and complicating the timing analysis. Matter along the wider line of sight also contributes extra gravitational influence that must be estimated. One particularly stubborn issue is that different mass distributions can reproduce similar image arrangements while predicting different cosmic distances. So astronomers combine high-resolution imaging, stellar motion measurements, environmental studies, and statistical modeling to reduce the ambiguity. The repeating quasar is therefore more than a visual curiosity. Each delayed image acts like a clock whose hands traveled through a different part of curved space-time. By comparing when those clocks deliver the same distant event, scientists can turn gravity's detours into a measurement of how the universe itself has been stretching. One quasar can show astronomers several different moments of its past at once. A telescope can capture 4 images of the same quasar in a single photograph, yet each image may be showing the quasar at a different moment in its own history. A quasar is the intensely bright central region of a distant galaxy, powered by matter heating as it falls toward a supermassive black hole. Its brightness can fluctuate as the accretion flow changes, making it a useful cosmic clock. When a massive galaxy lies between the quasar and Earth, the foreground gravity can redirect the quasar's light along several separate routes. Those routes do not have equal lengths, and they do not pass through identical gravitational environments, so the light forming one image may arrive days, months, or even years before the light forming another. In one observation, astronomers might therefore see one image of the quasar before a flare, a second while the flare is growing, and another after it has faded, even though all the images are received by the telescope on the same night. The sky is not duplicating the quasar in real time. It is placing several delayed records beside one another. This allows astronomers to do something almost like prediction. If a distinctive change appears first in the image with the shortest route, they can estimate when the same change should emerge in the later images and prepare telescopes to watch for it. Quasars are not perfectly simple clocks, because stars in the foreground galaxy can further magnify small regions of the quasar independently, changing one image without producing the same variation in the others. Researchers must separate these microlensing effects from changes that genuinely began in the quasar itself. Once they do, the multiple images become a remarkable study of an environment far too small and distant to resolve directly. Variations can reveal the scale of the glowing accretion disk, the motion of hot material near the central black hole, and the way different wavelengths emerge from different regions. A lensed quasar is therefore not merely one object copied across the sky. It is one changing source delivered through several clocks, allowing a single photograph to hold neighboring versions of the same distant past. What appears simultaneous to your telescope may have been separated by months at the source, reminding you that the sky does not arrange history in one clean layer. It folds different pages together and lets gravity decide which page reaches you first. A photon may spend thousands of years escaping the sun before reaching Earth in minutes. The sunlight warming your face completed the final journey from the sun in only about 8 minutes, yet the energy behind it may have begun struggling outward long before human civilization existed. Deep in the solar core, Nuclear fusion converts hydrogen into helium and releases energy initially in extremely energetic forms, including gamma rays. But the sun's interior is not transparent. It is an extraordinarily dense plasma filled with electrons and atomic nuclei, so radiation cannot travel outward in a straight line as it does after leaving the surface. A photon may move only a short distance before being scattered, absorbed, or transformed through an interaction with matter. New photons are then emitted in different directions, only to encounter more particles moments later. The energy follows a random walk, repeatedly changing direction and gradually being redistributed among enormous numbers of lower energy photons. Because of this, the escape is not one heroic photon traveling intact from the core to the surface. The original gamma-ray photon is usually destroyed during interactions, and its energy is passed through a long chain of absorptions, emissions, and scatterings. Estimates of how long this radiative diffusion takes vary with the solar model and with exactly what is being tracked, but the journey is commonly placed somewhere from many thousands to hundreds of thousands of years. In the outer layers, convection becomes important. Hot plasma rises, cools near the surface, and sinks again, transporting energy through moving matter rather than radiation alone. Only when the energy reaches the visible surface, the photosphere, can photons finally stream freely into space. From there, the trip to Earth is astonishingly direct and brief. This contrast allows scientists to observe two different versions of the sun. Sunlight tells you about energy that has spent an immense time working its way outward, while neutrinos created during fusion interact so weakly that they escape the solar interior almost immediately and reach Earth minutes later. Neutrino detectors therefore provide a far more current report of what the core is doing than visible sunlight does. The glow above you is not fresh news from the center of the sun. It is ancient interior energy that has been broken apart, shared, cooled, and rebuilt countless times before finally becoming the light you see. The last 8 minutes are the simplest part of its history. The true journey happened inside the star, where progress was measured not in speed, but in almost endless redirection. Gamma-ray burst test whether all light energies obey the same speed limit. For a few violent seconds, a gamma-ray burst can turn a remote region of the universe into a laboratory large enough to test whether nature gives every photon exactly the same cosmic speed. These bursts are among the most energetic explosions known, commonly associated with the collapse of massive stars or the mergers of compact objects. They can release photons spanning a vast range of energies, from lower energy radiation to gamma rays energetic enough to challenge the limits of space-based detectors. Some speculative theories of quantum gravity suggest that space-time may not be perfectly smooth at the smallest imaginable scale. If it possesses a hidden microscopic structure, extremely energetic photons might interact with that structure slightly differently from lower energy photons, producing a tiny difference in their travel speeds. No experiment across a laboratory table could easily detect such a minuscule effect, but a gamma-ray burst may lie billions of light years away. Over that enormous journey, even an almost unmeasurable speed difference could accumulate into a noticeable delay. Astronomers therefore compare when photons of different energies arrive and search for a pattern in which higher energy light is consistently early or late. So far, observations have found no convincing evidence that vacuum light speed depends on photon energy, placing severe limits on many proposed violations of relativity. The test is not as simple as comparing two arrival times, because the explosion itself may emit different energies at different moments. A high-energy photon arriving later might have traveled at exactly the same speed, but been produced later inside the burst. Scientists address this by examining extremely rapid features in the signal, comparing many bursts at different distances, and testing whether any delay grows in the way a propagation effect should. Particularly short and distant bursts are valuable because they combine sharp timing with a very long cosmic baseline. These studies also test Lorentz invariance, the principle that the basic laws of physics do not select a preferred state of steady motion. If light of different energies moved at detectably different vacuum speeds, that symmetry would require revision. Gamma-ray bursts have not yet revealed such a crack. Instead, photons with enormously different energies continue to arrive with an agreement so precise that many once plausible models have been ruled out or pushed towards scales far beyond direct reach. A distant explosion lasts only moments, but its light spends billions of years conducting the experiment. By the time those photons strike a detector near Earth, their near-simultaneous arrival has become a message not only about the star that died, but about whether spacetime treated every color of its final scream by the same rule. Neutrinos travel almost as fast as light, but not exactly. A particle can pass through an entire planet almost untouched, arrive from the heart of an exploding star, and still lose a race against light by an amount so small that only the universe itself provides a long enough track to notice. Neutrinos are among the lightest known particles, electrically neutral and so reluctant to interact with matter that trillions pass through your body every second without leaving a detectable trace. For decades, physicists wondered whether they might be completely massless, which would force them to move at exactly the vacuum speed of light. But experiments revealed that neutrinos can change from one type into another as they travel, a phenomenon called neutrino oscillation. And this transformation requires differences in their masses. Their exact individual masses remain difficult to measure, yet they are not all zero. Because neutrinos possess mass, however tiny, they must travel slightly below light speed. At the high energies common in astronomy and particle experiments, the difference is astonishingly small. A neutrino can move so close to the cosmic limit that over ordinary distances light gains almost no measurable lead. One of the most important natural tests came from supernova 1987A, whose neutrinos crossed roughly 168,000 light-years before reaching detectors on Earth, only a few hours before the supernova became visibly bright. That early arrival did not mean the neutrinos outran light. They escaped from the collapsing stellar core before visible radiation could fight its way through the surrounding layers, so they began their journey earlier. Their near-coincident arrival after such an immense distance showed that their speed was extraordinarily close to light's. In 2011, an experiment briefly appeared to find neutrinos arriving faster than light, creating worldwide excitement, but the result was later traced to equipment problems, including a faulty fiber optic connection and timing calibration issues. The episode became a useful reminder that extraordinary measurements demand relentless checking. Neutrinos remain remarkable without violating relativity. Because they interact so weakly, they carry information directly from places light cannot easily escape, including the center of the sun, nuclear reactors, violent cosmic explosions, and perhaps environments surrounding black holes. Their tiny mass also affects the formation of large-scale cosmic structure, because fast-moving neutrinos do not gather under gravity as readily as slower matter. These ghost-like particles therefore live between two familiar categories. They are not massless messengers like photons, yet they move so quickly that the distinction is almost invisible. Their slight delay tells you that nature can hide a real difference beneath extraordinary closeness, and that sometimes the smallest known mass is enough to keep even the most elusive traveler from sharing light's exact path through space-time. Cosmic ray particles cross the galaxy while experiencing far less time than we do. Some particles enter the Milky Way carrying so much energy that a journey lasting thousands of years by human clocks may occupy only a tiny fraction of that time along the particle's own path. Cosmic rays are not rays of light, but fast-moving pieces of matter, mostly protons and atomic nuclei, launched by powerful astrophysical environments such as supernova remnants, pulsars, stellar winds, and perhaps the regions around active black holes. Magnetic fields twist their trajectories, making it difficult to trace many of them back to their sources. Yet the most energetic cosmic rays move so close to light speed that their relativistic behavior becomes extreme. From Earth's perspective, a particle crossing a large part of the galaxy may spend tens of thousands of years in flight, but the proper time accumulated along that particle's route can be dramatically smaller. This does not mean the particle watches an external clock accelerate in one simple universal way, and it does not possess human awareness with which to experience the journey. It means that a hypothetical clock traveling with the particle would record far less elapsed time between emission and arrival than clocks approximately at rest with the galaxy. At extreme energies, the difference can become astonishing. A galactic distance that appears enormous in our frame is greatly contracted along the direction of the particle's motion. This allows unstable particles or nuclei to cross distances that would otherwise seem impossible within their own natural timescales, although collisions with radiation and interstellar matter can still destroy or transform them. Cosmic rays reveal their presence when they strike Earth's atmosphere and produce enormous cascades of secondary particles. A single incoming nucleus can collide with an air molecule high above the ground, creating a shower that spreads across kilometers and reaches detectors as a coordinated storm of electrons, photons, muons, and other fragments. The original particle may have carried the kinetic energy of a rapidly thrown object while compressed into one atomic nucleus, making the rarest ultra-high energy events far more energetic than anything human accelerators can produce in a single particle. Yet even these particles never reach light speed because they still have mass. Adding energy brings them closer and closer to the limit, while producing almost no visible increase in speed. Instead, the relativistic difference between our elapsed time and theirs becomes more severe. Their motion turns the galaxy into two different journeys at once, an ancient crossing measured by stars and planets, and a much shorter interval measured along the traveler's own route. When one of these particles finally collides above you, it may be ending a voyage that began before recorded history on Earth, while carrying almost none of that vast duration in its own accumulated time. Cosmic rays therefore arrive not only as fragments from distant astrophysical engines, but as physical evidence that the age of a journey is not stored in the distance alone. It also depends on the path and speed of whatever crosses it. Fast-moving muons reach Earth's surface because their internal clocks run slowly. High above your head, particles that should vanish long before reaching the ground are completing a journey that ordinary, non-relativistic reasoning says they cannot survive. Muons are unstable relatives of electrons, produced in large numbers when energetic cosmic rays collide with molecules in the upper atmosphere. Once created, a muon at rest survives on average for only about 2.2 microseconds before decaying into other particles. Even if it could move at nearly the speed of light for that entire interval, a simple calculation without relativity would allow it to travel only around 660 meters. Yet atmospheric muons are commonly created many kilometers above Earth, and enormous numbers of them still reach detectors at sea level. Their survival is not a minor correction or a statistical accident. It is one of the clearest natural demonstrations that moving clocks do not accumulate time in the same way as clocks in the laboratory frame. From Earth's perspective, the Moon is traveling at an extreme speed, so its internal processes, including the process governing its decay, unfold more slowly. Its average lifetime in our frame becomes long enough for it to cross the atmosphere before disintegrating. The phrase "its clock runs slowly" does not mean the muon is malfunctioning. Any imaginary clock traveling beside it would tick normally, and its decay would feel no more delayed than a resting muon's decay does in a laboratory. The difference appears when the muon's elapsed time is compared with ours. There is also a second, equally valid description. In the muon's frame, its lifetime remains the usual 2.2 microseconds, but the atmosphere is contracted along the direction of motion. The distance from its birthplace to the ground is therefore much shorter, allowing Earth's surface to reach the muon before it decays. These explanations are not rival stories. They are the same relativistic geometry described from two frames. Scientists have verified the effect by comparing muon counts at high elevations and near sea level. Without relativistic time dilation, the number surviving to lower altitudes would be drastically smaller than what instruments record. Muons now serve practical roles as well, because they penetrate dense material more effectively than many other charged particles. Detectors can use naturally occurring cosmic muons to image the interiors of volcanoes, pyramids, damaged reactors, and other structures too large or shielded for ordinary X-rays. The same particles whose survival once exposed a strange feature of time can now reveal hidden chambers and dense regions inside matter. Each moon reaching the ground is therefore a tiny experiment completed by the atmosphere itself. It begins in a violent collision overhead, carries a lifetime that seems far too brief for the distance ahead, and arrives only because distance and duration rearrange themselves around extreme motion. You do not need a spacecraft near light speed to see relativity operating. Its evidence is already falling through your body, born in the sky and surviving long enough to prove that even a particle's final moment depends on how fast it moves. Particle accelerators can approach light speed, but can never complete the final step. Inside the world's largest particle accelerators, protons travel so close to light speed that completing thousands of laps each second barely makes them any faster, no matter how much additional energy the machines provide. An accelerator does not push particles with a mechanical force, like an engine pushing a vehicle. Electric fields inside carefully timed radio frequency cavities give charged particles repeated bursts of energy, while powerful magnets bend and focus their paths so they remain inside a narrow vacuum tube. Early in the acceleration process, each burst produces a noticeable increase in speed. Soon, however, the particles approach the relativistic limit and their behavior changes. At the Large Hadron Collider, protons move at more than 99.999999% of light speed, yet they never reach the exact value. Engineers continue adding enormous amounts of energy, but that energy increasingly appears as greater momentum and collision power rather than a meaningful rise in velocity. This is precisely what researchers want. The goal is not merely to make particles fast. It is to concentrate enough energy into tiny collisions to create conditions that have not existed naturally since the early universe. When two beams meet, their motion can be converted into showers of new particles, allowing scientists to study the fundamental ingredients of matter and the forces acting between them. The final step to light speed remains forbidden because a proton possesses rest mass. Reaching the limit would require its energy to grow without bound, so no larger tunnel, stronger magnet, or more advanced power source could complete that last fraction. Even an accelerator surrounding a planet would encounter the same barrier. Practical machines face additional restrictions long before infinity becomes relevant. Curved trajectories make some charged particles radiate energy, magnets have finite strength, and beam stability becomes increasingly difficult. Electrons lose especially large amounts of energy when bent, which is why some electron accelerators use straight designs instead of giant rings. Protons radiate less and can circulate efficiently, but they still cannot become light. The achievement of an accelerator is therefore not that it defeats nature's limit, but that it approaches the limit closely enough for speed to stop being the main story. The particle keeps receiving energy while its velocity seems almost frozen, turning the impossible final step into a doorway through which entirely new forms of matter can briefly appear. Near light speed, added energy produces less additional speed. There comes a point where pouring more energy into a moving particle barely changes how fast it travels, even though the energy stored in its motion continues to rise dramatically. In ordinary life, speed and energy seem to grow together in a familiar way. Press harder on an accelerator and a car moves noticeably faster. That intuition works only when velocities are tiny compared with light speed. As an object approaches the cosmic limit, each new increase in speed demands disproportionately more energy than the one before it. A particle moving at 90% of light speed can still be accelerated, but pushing it to 99% requires a much larger investment. Moving from 99% to 99.9% costs far more again. even though the numerical change in speed looks smaller. The energy is not disappearing, and the particle is not secretly refusing the push. Its momentum becomes increasingly difficult to change, and relativity reshapes the relationship between energy and velocity so that the limit can be approached forever without being reached. This produces an effect that might be called speed saturation. The velocity displayed on an imaginary speedometer changes less and less, while the consequences of the added energy become more violent. A high-energy proton striking matter can create many new particles, penetrate deeply, or transfer enormous momentum even though its speed differs only slightly from that of a much less energetic proton. This is why knowing that two particles both move almost at light speed tells you surprisingly little about how energetic they are. One may carry thousands of times more energy than the other, while traveling only an almost imperceptible amount faster. The distinction matters in cosmic rays. Accelerator design, radiation shielding, and astrophysical jets, where tiny differences below the speed limit can correspond to enormous differences in destructive or creative power. It also corrects the misleading idea that an advanced engine could eventually overcome the barrier through patience alone. Continuous acceleration would keep increasing the traveler's energy, but the remaining gap in speed would shrink without ever vanishing. Nature does not place a wall at a location you suddenly collide with. Instead, it makes the road increasingly expensive until the destination recedes behind an infinite demand. Near light speed, energy stops expressing itself mainly as more velocity and begins revealing how deeply motion is tied to the geometry of space-time. Electricity and magnetism become different views of the same force under relativity. Magnetism can appear where another observer sees mostly electricity, suggesting that two forces taught separately in school are actually different perspectives on one electromagnetic reality. Consider a long wire carrying an electric current. In the laboratory, the wire may be electrically neutral overall because its positive atomic lattice and moving electrons balance one another, yet a nearby moving charge can feel a magnetic force. Now imagine observing the same situation while traveling alongside the moving electrons. In this new frame, the electrons may appear nearly stationary while the positive charges in the wire move in the opposite direction. Relativity changes the measured spacing between moving charges along the wire, altering their apparent charge density. The balance that looked neutral in the laboratory can become slightly unequal in the moving observer's description, producing an electric force where the laboratory observer described a magnetic one. Both observers predict the same physical motion for the nearby charge once their measurements are translated correctly. Neither field is fake. The electric and magnetic components simply mix when you change your state of motion, much as space and time mix between observers without losing their place in one larger structure. This is why a stationary electric charge produces an electric field, while that same charge viewed from a moving frame can also be associated with a magnetic field. Magnetism is not merely an illusion caused by relativity, because magnetic effects are measurable and carry energy, but relativity reveals why electricity and magnetism cannot be fundamentally separated. They are components of one electromagnetic field, and the division between them depends partly on how the observer moves. This unity had already begun to emerge from Maxwell's equations before Einstein developed special relativity. Those equations predicted electromagnetic waves moving at one fixed speed, creating a tension with older ideas of absolute space and time. Relativity resolved the tension by showing that the laws of electromagnetism remain consistent for all steadily moving observers because their measurements of distance, duration, electric fields, and magnetic fields transform together. Motors, generators, radio antennas, and transformers all rely on this joined behavior. But the deeper meaning reaches beyond technology. What you call an electric force in one frame may contain magnetism in another, and what seems like two separate influences is one field viewed from different directions through space-time. Motion does not merely change how fast an object appears to travel. It can change which aspect of a fundamental force becomes visible. Changes in an electric field cannot spread instantly. Switch on a powerful electric source, and the universe does not update its field everywhere in the same instant. The change begins locally and travels outward through space. An electric field describes how a charged object would influence other charges around it. But this influence is not an invisible, rigid structure attached to the source across unlimited distance. If the source charge moves, accelerates, or changes its arrangement, nearby space responds first, while more distant regions continue behaving according to the earlier state until the disturbance reaches them. Maxwell's theory of electromagnetism revealed that changing electric and magnetic fields sustain one another as they propagate, forming electromagnetic waves. Visible light is one example, but the same physics includes radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. This means that when an antenna begins oscillating electrons, it does not immediately create a completed wave across the entire landscape. The disturbance expands outward, crossing the room, then the city, then increasingly distant space. A detector responds only when the changing field physically arrives at its location. Static-looking electric fields obey the same deeper principle. If you could somehow alter a charge, an observer far away would continue measuring the old field for a while, because the new information has not yet reached them. This is essential for causality. If electric fields changed everywhere instantly, you could encode information into a charge's motion and have distant detectors respond with no travel time, creating a method of instantaneous communication. Nature prevents this by making every change propagate at the same fundamental causal speed as light in vacuum. Near an accelerating charge, the field can be complicated, containing regions that remain closely connected to the charge's immediate behavior and radiation that can escape to great distances. But none of these regions receives knowledge from the future. Each point responds only to the source as it was when the relevant influence began its journey. The electric field surrounding you is therefore not a perfectly current portrait of every charge in existence. It is a layered record assembled from signals of different ages, with nearby changes arriving quickly and remote changes still traveling. What appears to be a single invisible field is actually a history continually spreading through space, ensuring that even electromagnetism must wait for reality to deliver the news. A charge begins moving before distant space can know it has moved. The moment an electron is forced into motion, its immediate surroundings begin to change, while distant space continues responding to a version of the electron that no longer describes what it is doing now. To understand why, imagine the electric field around a stationary charge as a pattern extending outward in every direction. This picture is useful, but the field lines are not physical strings that can be pulled from one end and become tense everywhere at once. When the charge accelerates, the nearby pattern adjusts first. Farther away, the field still points and behaves according to the charge's earlier position and motion. Between these regions lies a traveling disturbance, a transition carrying the new information outward. Physicists describe the field at a distant location using the charge's retarded position. Not where the charge is at the moment the field is measured, but where it was when the influence now arriving began its journey. This delayed relationship prevents distant space from tracking the charge instant by instant. Acceleration also produces electromagnetic radiation. A charge moving steadily does not continuously radiate merely because it is in motion, but when its velocity changes, part of the disturbance can detach from the near field and continue outward as a self-propagating wave. The energy in that radiation must come from whatever force accelerated the charge. This is why radio antennas require electrical power. Electrons are driven back and forth. Their changing motion reshapes the surrounding electromagnetic field, and part of that changing field escapes into space. The distant detector is not feeling the electron's current action through an instantaneous link. It is receiving an old consequence of that action. Even after the electron stops moving, some regions farther away will temporarily continue behaving as though the earlier acceleration has not yet ended. because the final update is still in transit. In principle, the outward moving disturbance can continue across interplanetary and interstellar space, becoming weaker as its energy spreads across a growing area, but never gaining the ability to arrive early. This creates a strange but precise image of reality. An object can already have changed while most of the universe remains physically committed to its past. The charge moves first, and knowledge of the movement follows afterward in an expanding shell. Distant space is not ignorant because it lacks intelligence. It is ignorant because no physical fact can become available before the messenger carrying that fact has crossed the distance. Every radio transmission is a message sent into the future. The instant your voice enters a radio transmitter, it stops belonging entirely to the present and begins traveling toward listeners who can only receive it later. A microphone first converts pressure variations in the air into an electrical signal. The transmitter then places that information onto an electromagnetic carrier by changing features such as its amplitude, frequency, or phase. An antenna drives charges in a carefully controlled rhythm, launching a radio wave outward through space. The wave may reach a nearby receiver in a fraction of a second, a satellite after a noticeable delay, or a distant spacecraft many hours later. In every case, the receiver encounters a preserved pattern created earlier at the source. Radio communication therefore never joins two locations in one perfectly shared moment. It allows one place to leave a physical influence that another place can decode in its own future. On Earth, the delay is usually small enough for conversation to feel live, but across the solar system, the hidden structure becomes obvious. Engineers commanding a distant probe must predict where it will be and what conditions it may face when the instruction finally arrives. The probe's reply then begins a second journey, so mission control receives not its present condition, but a report from the past. Radio also changes as it travels. Its energy spreads over a growing area, making the signal weaker with distance. Gas, plasma, planetary atmospheres, human technology, and natural cosmic sources can add noise or distort parts of the transmission. Powerful antennas, narrow beams, error-correcting codes, and sensitive receivers help recover information, but they cannot prevent the wave from fading. This is why Earth's ordinary broadcast leakage is unlikely to remain an easily recognizable television program across enormous interstellar distances. Much of it becomes extraordinarily weak and difficult to distinguish from background noise. Deliberately aimed transmissions using large antennas would be more detectable, but even those messages would reach another star only years after they were sent. Any reply would require at least the same journey back. A conversation across 50 light-years could not complete one simple exchange in less than a century. The sender might be gone before the answer arrived, and the receiver would be responding to a society that had already changed. Every radio signal is therefore a small act of trust in time. You release an organized pattern into space without knowing who, if anyone, will receive it, or what world will exist when it arrives. The transmission does not carry your present with it. It carries evidence that your present once existed, turning communication into a message addressed not merely to somewhere else, but to a future that begins the moment the signal leaves. A perfectly rigid object cannot exist because forces need time to travel through it. The idea of a perfectly rigid object hides an impossible demand. Every part of it would have to respond to a force at exactly the same instant, no matter how far apart those parts were. In everyday life, a stone, a steel beam, or a glass plate can appear rigid because its deformation is too small and too fast for your eyes to notice. But at the atomic level, none of these objects behaves as one indivisible whole. Matter is held together by electromagnetic interactions between atoms, and when you push one region, you first disturb only the atoms nearest your hand. They shift slightly from their equilibrium positions, changing the forces acting on neighboring atoms, which then disturb the next layer. The instruction to move travels through the object as a mechanical wave rather than appearing everywhere at once. A truly perfect, rigid body would have to transmit that instruction infinitely fast. allowing the far side to react before any physical signal could reach it. Such an object would become an instant communication device. Move one end here and a distant end would respond without delay. Relativity forbids this because information cannot propagate infinitely quickly. Even extremely stiff substances only transmit disturbances at a finite speed determined by their density, bonding, temperature, and internal structure. Rigidity is therefore not an absolute property but a comparison between timescales. An object seems rigid when internal signals cross it much faster than the motion you are observing. The illusion can fail dramatically under extreme conditions. A long, rotating structure cannot be accelerated into motion, as though every section already knows the correct speed, and a large spacecraft cannot change direction without stresses passing through its frame. Engineers must allow materials to flex because attempting to suppress all deformation would not create perfect rigidity. It would merely concentrate stress until something fractured. Relativity even requires care when defining a body that maintains constant distances between neighboring parts during acceleration, because different sections may need to accelerate at different rates to preserve the structure. The deeper lesson is that an object is never simply there as one instantaneous unit. It is a community of particles continually communicating forces across finite distances. What you call solidity is the successful coordination of countless delayed responses, fast enough to feel unified, but never fast enough to become truly immediate. The far end of a metal rod does not move the instant you push the near end. Push one end of a long metal rod, and for a brief interval, the far end remains perfectly unaware that anything has happened. Your hand first compresses the metal nearest the point of contact, moving those atoms a tiny distance closer together. Because atoms resist being forced away from their preferred spacing, this compressed region pushes on the next region, which pushes on the next, creating a stress wave that travels along the rod. Only when that wave reaches the far end does the final section begin to move. In steel, such disturbances travel at several kilometers per second, extremely fast by human standards, yet vastly slower than light. In a short household object, the delay is measured in millionths of a second and seems non-existent. But in a rod hundreds or thousands of kilometers long, the interval would become obvious. You could push the near end, release it, and wait while the far end continued resting before receiving the mechanical message. During that waiting period, the rod would not move as one solid block. It would be slightly compressed near you, with the deformation spreading forward through the material. The exact speed depends on the rod's stiffness and density. Strong atomic bonds help disturbances travel quickly, while greater inertia tends to slow the response. Temperature, imperfections, shape, and whether the wave is stretching, compressing, twisting, or bending the rod can also change how it propagates. Some of the energy may reflect when it reaches an end, or a boundary between different materials, producing echoes that bounce through the rod. This is closely related to how sound travels through solids, because sound is itself an organized vibration passed from particle to particle. The electrons in the metal help establish the bonds that make the material stiff, but they do not cause the whole rod to jump forward instantly. What moves through the rod is not a command transmitted by one atom across the entire length. It is a local sequence of forces. This matters in bridges, buildings, railway tracks, spacecraft, and industrial machinery, where impacts can send stress waves through structures and create damage far from the original contact point. The rod that feels perfectly solid in your hand is therefore briefly divided into regions with different information about the push. Its near end has entered a new state, while its far end still belongs to the old one, until the traveling compression finally brings both ends into the same physical story. If light were much slower, everyday life would be filled with visible delays. Imagine looking across a room and watching someone's smile appear noticeably after you saw them begin to react. Not because your brain was slow, but because their light had not yet finished crossing the distance between you. If light traveled at the speed of a car, a sound, or even a fast aircraft, Ordinary life would become a landscape of visible lateness. A mirror would no longer follow you smoothly. You might turn your head, pause, and then watch your reflection perform the movement you had already completed. Standing at one end of a street, you would see vehicles where they had been moments earlier, making movement appear detached from present reality. Sports would become almost impossible to judge from a distance because the ball, the players, and the scoreboard would each be seen according to how far their light had traveled. A person standing close to you would appear more current than someone across a field, so one scene would contain many different visible times at once. Sound might arrive before sight if light were slowed enough, reversing one of the most familiar features of thunderstorms and fireworks. Communication screens would add another layer of delay. A camera would first wait for light from the subject, then electronics would process the image, and the transmitted signal would travel onward at the same reduced limit. Even local conversation could feel like communication across another world. Driving would require prediction rather than reaction, because the road ahead would always be seen as it was earlier. Fast-moving objects might appear in positions they had already left, and collisions could occur before a distant witness saw the motions that produced them. Shadows would crawl visibly as illumination spread across a room, while switching on a lamp would create an expanding boundary of brightness rather than instant light. Astronomy would become even stranger, but the most dramatic difference would be psychological. You would grow up knowing that vision never offered anything close to immediacy. Distance would be experienced not merely as space, but as an obvious layer of time separating you from everything you saw. Human architecture might favor smaller rooms and closer communities simply because visual coordination worsened with separation. Technology would place processors, sensors, and decision systems as near as possible to the events they controlled. Yet a much slower light speed would also change far more than perception, because that speed is woven into electromagnetism, relativity, atomic structure, and the relationship between space and time. Reducing it while leaving everything else unchanged is not a fully realistic physical possibility. The thought experiment is valuable precisely because it exposes what the actual speed normally hides. Your world feels visually immediate not because light arrives instantaneously, but because it is so fast that distance has been concealed from your senses. Slow it enough, and every glance would reveal the delay that has always existed between reality and the image reaching you. If light traveled infinitely fast, space and time would not behave as they do. Remove the finite speed of light from the universe, and you do not merely make lamps illuminate rooms more quickly. You dismantle the structure that forces space and time to behave as one connected reality. In the mathematical limit where the causal speed becomes infinite, any signal could cross any distance with no delay, so every observer could agree on one universal present extending across the cosmos. Clocks moving relative to one another would no longer need to disagree in the relativistic way. Lengths would not contract because of motion, and the ordering of distant events could be placed onto a single absolute timeline, resembling the older Newtonian picture of the universe. Space would become a stage existing independently of time, while time would pass at the same rate everywhere, untouched by ordinary motion. But this apparently simpler world would lose many of the relationships that hold modern physics together. Electricity and magnetism are unified, partly because changes in their fields propagate at a finite speed. If electromagnetic influence were instantaneous, the equations describing radiation, antennas, and light waves would have to be fundamentally different. A photon could not remain the same kind of physical object while simply being assigned infinite speed, because its energy, momentum, wavelength, and relationship with matter belong to a theory built around a finite causal constant. Even cause and effect would become strangely global. A distant star could alter what happens around you at the exact instant it changed, leaving no traveling signal and no expanding boundary, separating informed regions from uninformed ones. Distance would still exist geometrically, but it would no longer create a delay in knowledge. The universe would possess no meaningful distinction between nearby and remote influence, and every physical system could, in principle, respond immediately to changes arbitrarily far away. Yet this thought experiment must be handled with care, because the speed of light is not an adjustable setting that can be changed, while every other law remains untouched. It acts as a conversion between measurements of space and measurements of time, appearing throughout relativity, electromagnetism, particle physics, and the behavior of matter. Making it infinite would require rebuilding those laws rather than merely speeding up illumination. The universe you know contains memory, horizons, delayed consequences, and observers with different measures of time because influence takes time to travel. An infinitely fast light would erase much of that architecture, creating a reality that might feel more intuitive, but would no longer resemble the one capable of producing the stars, atoms, and moving clocks around you. The finite speed is therefore not an inconvenience added to space and time. It is part of what gives them their present form. Hypothetical tachyons would create severe problems for causality. Suppose a particle existed that could never move slowly enough for light to catch it, a traveler born permanently on the forbidden side of the universe's speed boundary. Such hypothetical particles are called tachyons, and they were once explored as possible faster-than-light entities within relativity. A tachyon would not behave like an ordinary particle that had simply been accelerated too far. In the mathematical description, it could never slow down to the speed of light or cross into the slower-than-light world, just as a massive ordinary particle cannot accelerate through the boundary from below. Its relationship between speed and energy would also appear deeply unfamiliar. Removing energy could make it move faster, while forcing it closer to light speed from above would demand ever more energy. Strange as that sounds, the most serious problem would not be the particle's motion itself. The danger would arise if tachyons could be produced, detected, and deliberately controlled as signals. Relativity allows observers moving differently to disagree about the time order of sufficiently separated events, and a faster-than-light transmission can connect events in a way that turns this disagreement into a causal reversal. One observer may describe a tachyon message as traveling forward in time from sender to receiver, while another valid observer may describe the reception as occurring before the message was sent. Add a return signal from a suitably moving receiver, and the original sender could obtain a reply before deciding to transmit anything. You might receive instructions warning you not to send the message responsible for those instructions, creating a loop with no consistent origin. Physicists have proposed interpretive tricks in which a tachyon traveling backward in time is redescribed as a different tachyon traveling forward. But this does not automatically rescue controllable communication from paradox. A stable theory would need a deeper rule preventing causal contradictions, perhaps by forbidding certain interactions or making usable tachyon signals impossible. No experimental evidence has shown that real particles travel through vacuum faster than light. There is also an important modern distinction. When quantum field theory describes a field as tachyonic, it usually does not mean that detectable particles are outrunning light. It generally means the assumed state of the field is unstable, like a bull balanced at the top of a hill, and the system will settle into a more stable configuration where ordinary excitations need not be superluminal. The word survives, but its meaning has changed. Tachyons remain valuable because they expose how tightly motion is tied to causality. The universe might tolerate equations containing faster-than-light possibilities, yet turning those possibilities into controllable messengers threatens the difference between explanation and prediction. A tachyon would not merely arrive early. It could make an event become responsible for preventing its own cause, forcing reality to answer a question that logic cannot ask consistently. A. Warp drive would move space itself, rather than locally outrunning light. The dream of a warp drive begins with a loophole that sounds almost too elegant. Instead of pushing a spacecraft through space faster than light, reshape the space surrounding it so the destination is carried closer. In 1994, physicist Miguel Alcubierre showed that Einstein's equations permit a mathematical geometry in which a compact region, often called a warp bubble, moves through the larger universe while the space ahead contracts and the space behind expands. A spacecraft resting inside the bubble would not locally race past nearby light beams. Within its immediate surroundings, it could remain nearly stationary and experience no ordinary violation of the local speed limit. Yet the bubble itself could, in the mathematical description, change its separation from distant locations at an effective rate greater than light, much as cosmic expansion can increase the distance between remote galaxies without forcing either galaxy to outrun a neighboring photon. This makes the idea fundamentally different from a conventional rocket. There would be no exhaust accelerating the ship across every kilometer of the route. The geometry of the route would be altered around it. But a valid solution to Einstein's equations is not automatically a machine that nature allows engineers to build. The original warp geometry requires regions with negative energy density, often described as exotic matter, arranged in a highly specific pattern around the bubble. Quantum physics can produce limited negative energy effects under special conditions, but nothing known suggests that the required amount, arrangement, or stability could be achieved on spacecraft scales. Some variations attempt to reduce the energy demands or change the geometry, yet they still face profound questions involving extreme stresses, bubble formation, control, and physical realizability. A superluminal bubble may also develop horizon-like boundaries that prevent the crew from sending instructions to the front edge from inside, raising the uncomfortable question of how travelers could create, steer, or stop the distortion once the journey began. Matter and radiation encountered along the path could be compressed or altered around the bubble, potentially creating hazardous effects when the field collapsed. And because effective faster-than-light travel can be combined with relative motion to form closed causal loops, a usable warp drive might inherit the same time travel problems that trouble every other superluminal route. None of this proves that every conceivable manipulation of spacetime is eternally impossible. It means the Alcubierre concept is presently a theoretical spacetime model, not a tested propulsion technology or a blueprint awaiting better materials. Its real importance lies in the question it forces you to ask. When relativity forbids an object from outrunning light locally, does it also forbid humanity from reshaping the road beneath that object? The equations offer a cautious mathematical opening, but the physical universe has not shown that the door can be built, powered, controlled, or crossed. Traversable wormholes could turn faster, travel into time travel. A shortcut through space becomes far more dangerous when its two entrances stop agreeing about what time it is. A traversable wormhole is a hypothetical tunnel connecting two distant regions of spacetime, with each opening usually called a mouth. If such a structure existed and remained open, entering one mouth might allow you to emerge from the other after crossing only a short internal distance, even when the mouths were separated by many light years in ordinary space. But the most unsettling possibility begins after the mouths are created. Suppose they initially sit beside one another with synchronized clocks. One mouth is then taken on a high-speed journey and returned, or placed for a long period near an extremely strong gravitational field. Relativity predicts that this traveling or deeply positioned mouth would accumulate less time than the mouth that remained elsewhere. The tunnel could still connect them internally, but the clocks outside the two openings would no longer show the same date. Walking through the wormhole might then carry you not only between locations, but between different external times. You could enter the younger mouth and leave the older one at a moment that, according to the outside universe, occurred before you entered. If the separation and time shift were arranged appropriately, an ordinary slower-than-light journey back to the starting point could complete a loop into your own past. This does not mean wormholes have been discovered, or that Einstein's theory promises engineers a time machine. Traversable examples are mathematical solutions built under highly unusual conditions. They generally require negative energy density or other forms of exotic stress to prevent the throat from collapsing, and quantum physics places severe restrictions on how much negative energy can exist, how long it can persist, and how it can be arranged. radiation passing repeatedly through a wormhole might also grow uncontrollably near the moment when a time loop begins, potentially destabilizing the structure before it becomes usable. Some calculations suggest that quantum effects could destroy the wormhole or prevent a chronology-violating region from forming, an idea related to Stephen Hawking's chronology protection conjecture, though no complete theory has proved that nature must always protect history in this way. A traversable wormhole would therefore be more than a tunnel cut through distance. Its two mouths would behave like clocks connected by a hidden corridor, and once those clocks age differently, the corridor could link two moments that the outside world insists should remain separate. The mystery is not simply whether space-time can be folded. It is whether the universe permits the fold to close upon its own past without tearing the logic of events apart. Faster-than-light routes could create loops, where information reaches its own past. The greatest threat posed by a faster-than-light route is not that a message arrives unusually early, but that several such routes can be arranged until the message returns before it was ever sent. Imagine two stations moving rapidly relative to one another, each equipped with a hypothetical communication system capable of transmitting information across space-like separation. One station sends a signal that, in its own frame, travels forward in time and reaches the other almost immediately. Because the stations do not share the same definition of distant simultaneity, the receiving station may describe the signal as arriving at a time that the first station considers earlier than expected. If the second station then sends a faster-than-light reply using its own frame, the return message can intersect the first station's history before the original transmission. The loop is complete. Information has entered its own past. You could receive a file instructing you not to send that file, a warning describing an accident that only occurs because you react to the warning, or the design for a machine that no person ever actually invented, because each generation copied it from the message received from the future. The first example creates a contradiction, while the last creates a bootstrap paradox in which information exists without a clear origin. These problems arise not because physicists have chosen an inconvenient convention for clocks, but because special relativity treats all inertial frames as physically valid. A superluminal signal that is forward-directed for one observer can connect events in an order that another observer reverses. One isolated shortcut placed inside a universe with a hidden preferred frame might avoid some of these loops, but then the symmetry at the heart of relativity would no longer be complete. Other proposed escapes include the Novikov self-consistency principle, which allows time loops only when every event fits into one contradiction-free history, or branching universe ideas in which changing the past creates a different history rather than rewriting the one that produced the traveler. These are possible interpretive responses, not experimentally confirmed laws. Quantum gravity may contain a deeper restriction that prevents any usable faster-than-light geometry from forming, or it may permit strange, self-consistent loops under conditions no civilization could control. What makes the problem so severe is that information does not need a human passenger to damage causality. A single controllable bit traveling around the correct loop would be enough. Faster-than-light travel promises to shorten distance. Yet relativity quietly transforms the shortcut into a circle, where the destination may lie not only ahead of the sender, but behind the decision to send anything at all. The quantum vacuum still respects the universe's causal speed limit. Empty space may contain restless quantum fields, fleeting fluctuations, and correlations stretching across enormous distances. But none of that activity provides a hidden channel for sending information faster than light. In quantum field theory, the vacuum is not absolute nothingness. It is the lowest energy state of fields that exist throughout space, and measurements performed in that state can reveal uncertainty, zero-point effects, and correlations between separated regions. This language often produces the misleading image of particles constantly appearing, traveling impossibly fast, and vanishing before nature can notice. Virtual particles, however, are mainly elements used inside calculations. They are not ordinary detectable particles secretly carrying messages outside the causal structure. The theory is built so that physical operations performed at locations too far apart to influence one another cannot be used to transmit a controllable effect. Technically, measurable quantities associated with space-like separated regions are arranged so that the order of local operations cannot create an observable causal contradiction. In simpler terms, what you choose to do in one laboratory cannot alter the statistics seen immediately in a distant laboratory before an ordinary light-speed signal could arrive. The vacuum can contain correlations, just as entangled systems do, but correlation is not communication. A distant detector may produce results related to yours when the data are later compared, yet its local sequence remains random and reveals nothing about which measurement you chose. Even the Casimir effect, in which closely spaced conducting plates experience an attraction related to the quantum electromagnetic field, does not imply instant action across space. The boundaries change which field patterns are allowed between and around the plates, producing a measurable difference in stress and energy. If one plate is moved, the altered conditions do not update the entire vacuum immediately. The resulting disturbance propagates causally through the field. Likewise, vacuum polarization around charges modifies how interactions appear, but it does not create a superluminal messenger. Quantum theory can make ordinary ideas of emptiness, particles, and locality feel incomplete, yet its experimentally successful form remains remarkably strict about usable influence. The vacuum may fluctuate without becoming a broadcast network, and it may connect probabilities without delivering chosen words. This distinction protects physics from a seductive mistake, assuming that anything strange, non-classical, or spread across space must be traveling faster than light. The quantum vacuum is not silent in the sense of being featureless, but it is silent in a more important way. It will not carry your message into a place where cause has not yet had time to arrive. The speed of light may reveal something fundamental about the structure of space-time. Perhaps light is not fast because of some special property carried by photons. Perhaps photons move as they do because they reveal the hidden geometry of the universe more clearly than anything else. In relativity, the constant commonly called the speed of light acts as a bridge between measurements of space and measurements of time. It tells physics how a duration can be compared with a distance and helps determine which events can be connected by physical influence. You can picture every event as surrounded by an invisible causal structure. Some future locations can be reached by slower objects. Some lie exactly along paths available to light, and others are too distant to influence without violating relativity. Photons follow those light-like paths because they are massless, but the paths would remain part of spacetime's geometry, even in a region containing no visible beam. This is why physicists often regard the constant not merely as the speed of one particular phenomenon, but as an invariant speed built into spacetime itself. The same structure appears in the equations governing electromagnetism, particle motion, gravity, and the transformation of measurements between moving observers. In modern physics, space and time are not separate containers loosely placed beside one another. They form a single framework whose causal shape is organized around this finite invariant scale. The constant also distinguishes three fundamentally different kinds of separation between events. Those that can share a cause and effect relationship, those connected only by a light signal, and those too widely separated for any causal exchange at that stage. This classification remains meaningful even when coordinates change and different observers describe distances or durations differently. Some attempts to build quantum theories of gravity suggest that spacetime may emerge from deeper relationships, information, or quantum connections, rather than being fundamental itself. If that is true, the invariant speed may eventually be understood as a large-scale consequence of an even deeper structure, much as the speed of sound emerges from the properties of a material. Yet no established theory has demonstrated that this is how nature works. For now, the constant stands at a strange boundary between explanation and assumption. It explains why causal structure takes the form we observe, while its own presence is accepted as part of the framework. Light may therefore be less like a runner obeying the rules of space-time and more like the visible trace of those rules, moving along the lines where distance and duration meet so perfectly that the architecture beneath reality briefly becomes observable. Scientists test whether the speed of light has always been the same. To ask whether light moved differently billions of years ago, scientists must first solve a subtle problem. The number assigned to its speed depends on the units used to measure distance and time. Today, the value of light's vacuum speed in meters per second is exact because the meter is defined using that value. So repeatedly measuring the same number cannot reveal whether the underlying laws of nature have changed. A more meaningful test looks for changes in dimensionless relationships, pure numerical ratios that remain the same regardless of whether lengths are measured in meters, miles, or any imagined alien unit. One of the most important is the fine structure constant, which describes the strength of electromagnetic interactions and depends on the relationship among light, electric charge, and quantum physics. Scientists compare extremely precise atomic clocks because different kinds of atoms would change their ticking rates differently if this electromagnetic relationship drifted over time. They also examine absorption patterns left in light from distant quasars. Gas clouds billions of years in the past absorbed specific wavelengths according to the atomic laws operating then, allowing those ancient patterns to be compared with laboratory measurements today. Other evidence comes from nuclear processes in the early universe. The cosmic microwave background, geological records, and violent astronomical events whose photons travel across enormous distances at widely different energies. If energetic photons consistently arrived earlier or later in a way that increased with distance, it could suggest that the causal behavior of light depends on energy or cosmic era. So far, no reliable observation has established that the local vacuum speed or the relevant dimensionless constants have changed. Some studies have reported intriguing hints, but systematic effects, such as wavelength calibration errors, unknown conditions inside distant sources, or assumptions about other constants, can imitate the signal. This is why scientists do not ask only whether one measured quantity appears different. They seek the same pattern using unrelated clocks, telescopes, particles, epochs, and experimental methods. Varying speed of light theories remain legitimate subjects of theoretical investigation, and some were proposed as alternatives or additions to inflationary cosmology, but they must specify exactly which physical quantity changes and how that change would become observable without being merely a redefinition of units. The question is therefore deeper than whether an ancient photon was numerically faster. It asks whether the relationships binding atoms, radiation, and space-time have remained unchanged throughout cosmic history. Every old spectrum becomes a preserved experiment, allowing matter that existed before Earth formed to testify about whether the rules governing light were already the same. No one yet knows why the universe has this exact speed limit. The famous number, 299,792,458 meters per second, looks like a code engraved into reality. But asking why nature selected those exact digits begins with a surprising correction. The digits themselves are largely a human choice. Since 1983, the vacuum speed of light has been assigned that exact value in the International System of Units, and the meter is defined from the distance light travels during a specified fraction of a second. If humanity had chosen different units for length or time, the numerical value would be different without changing the universe at all. Physicists can even choose natural units in which the speed of light is simply written as 1. The profound mystery is therefore not why the constant contains those particular decimal digits. It is why reality possesses a finite invariant speed at all, why that speed organizes causality, and why its relationship with other physical constants produces the dimensionless numbers found in nature. The Standard Model and relativity use fundamental constants as inputs measured from the world. They describe with extraordinary precision what follows from those values, but they do not fully explain why every value takes the form it does. A future theory uniting gravity with quantum physics might derive today's constants from a deeper mathematical structure, a symmetry, an early universe phase transition, or the stable state of more fundamental fields. Another possibility is that different regions or universes could possess different effective constants, with observers naturally appearing only where the resulting laws permit complex structures. That idea may help frame the question, but it does not yet provide a tested mechanism or a unique prediction. It is also possible that the invariant speed is not an independent ingredient, but emerges from a deeper layer in which ordinary space and time do not yet exist. In such a theory, asking why the speed has its value might resemble asking why sound travels at a certain speed before understanding atoms and elasticity. The answer would lie in hidden constituents and relationships. Yet this remains speculation. Modern science can explain why massive objects cannot reach the invariant speed, why all local observers measure it consistently, and how it shapes electromagnetic waves and causal order. What science cannot currently provide is a final reason that the universe must contain precisely this causal structure rather than another. The last mystery is therefore quieter than the number printed in textbooks. Humanity has fixed the number by defining its rulers, but nature fixed the relationship long before rulers existed. We know how to use that relationship to measure the cosmos, while still not knowing whether it is a basic fact with no deeper explanation, or the visible surface of a law we have not yet discovered.